Hello and welcome to The Sleepy Scientist. If you enjoy calm, carefully explored science that helps you unwind while gently expanding the edges of what you know, take a moment to like the video and subscribe to the channel. And before settling in, share where you're watching or listening from tonight. A city apartment, a quiet village, somewhere near the ocean, or perhaps on the other side of the planet entirely. It is a small detail, but in a story about distance and connection, it feels quietly appropriate. Because tonight's question begins with distance. Two particles are created together. They drift apart. One moves left, the other right. They may end up separated by meters, by kilometers, even by the span between continents. And yet, when one is measured, the other responds with a correlation that appears immediate. No signal travelling between them, no visible tether, no classical mechanism connecting their behaviour. How can distant things stay connected? This is not a metaphor. It is not poetry, and it is not speculation. It is a feature of quantum mechanics known as quantum entanglement, and it has been tested in laboratories across the world, from optical benches in Europe to satellites orbiting high above the Earth. The word entanglement was introduced by Erwin Schrodinger in the 1930s. He believed it was not a side effect of quantum theory, but its defining characteristic. Albert Einstein famously disliked the implication, describing it as spooky action at a distance. For him, physics was supposed to describe a world made of separate parts, each with its own properties, influenced only by nearby events. Quantum theory suggested something else. It suggested that under certain conditions, two systems cannot be described independently at all. They share a single mathematical state. Even when separated in space, their physical descriptions remain intertwined. This challenges something so basic that it often goes unnoticed, the assumption that objects possess their own independent realities, that what happens here is not structurally linked to what happens far away unless something physically travels between them. And yet, experiment after experiment has confirmed the predictions of quantum mechanics. Carefully designed tests, beginning with the work of John Bell in the 1960s, and refined through decades of increasingly precise measurements, have shown that nature does not behave according to local hidden variable theories. The correlations observed exceed what classical realism allows. Still, nothing travels faster than light. No usable signal crosses the gap. Relativity remains intact. The universe does not break its own speed limit. Instead, something subtler is happening. Quantum entanglement suggests that what we call separate may not be as fundamental as it seems. That connection may arise not from communication, but from shared structure, from a common origin in a deeper mathematical description of reality. Tonight, the journey will move carefully, beginning with the classical assumption of separability. Then exploring how quantum theory redefined what a physical state even is. From there, into the historical debates between Einstein and Schrodinger. Through Bell's theorem and the experiments that followed. Into modern ideas about information, entropy, spacetime geometry, and even the possibility that the fabric of space itself may emerge from patterns of entanglement. There will be no sensationalism, no mysticism, only careful steps through ideas that are strange precisely because they are true. So wherever you are listening from, perhaps thousands of kilometers from someone else hearing the same words, consider this quiet thought. Distance may not mean what it once meant, and connection may run deeper than the space between. For most of scientific history, the universe was assumed to be built from separate things. Solid bodies moved through space, planets orbited stars, cannonballs followed curved paths through the air. Each object possessed its own position, its own velocity, its own mass. If something changed, there was a reason nearby. A push, a pull, a collision. A cause that touched it directly or reached it through a force. This assumption is known as separability. It is the idea that physical systems have their independent states. What happens here is determined by what is here, plus whatever arrives from outside in a continuous, traceable way. In the 17th century, Isaac Newton gave this worldview mathematical precision. His laws of motion described how forces change motion. His law of universal gravitation explained how masses attract each other across space. Gravity acted at a distance, yes, but even in Newton's framework, each object still had its own definite position and momentum at every moment. The Earth did not lose its individuality simply because the sun pulled on it. It remained a distinct body with its own evolving state. By the 19th century, James Clerk Maxwell unified electricity and magnetism into a field theory. Instead of mysterious action at a distance, Maxwell described electromagnetic fields filling space continuously. Charges influenced the field locally. Changes in the field propagated outward as waves at a finite speed. Those waves turned out to be light itself. Maxwell's equations implied that electromagnetic disturbances travel at a fixed speed, approximately 300,000 kilometers per second. Later measurements refined this number with extraordinary precision. But the central idea remained simple and powerful. Influences do not leap instantaneously from one place to another. They spread through space in a continuous way. Then, in 1905, Albert Einstein formalized this principle in the theory of special relativity. The speed of light in vacuum became not just a property of electromagnetism, but a fundamental limit of nature. No signal, no information, no causal influence can travel faster than light. Events separated by enough distance cannot affect one another instantaneously without violating the structure of spacetime itself. Locality in this context means that physical influences are mediated through nearby interactions, and that signals are constrained by the geometry of spacetime. If two events are separated in such a way that light could not travel from one to the other in time, then no physical cause can link them in that interval. This principle is woven deeply into modern physics. It underpins particle accelerators, satellite communications, and the global positioning system, which must account for relativistic corrections to remain accurate within meters. So by the early 20th century, physics rested on two pillars. First, separability. Systems possess their own properties, definable independently of distant systems. Second, locality. Influences propagate no faster than light, through continuous physical processes. These principles feel almost self-evident. After all, if two coins are placed on opposite sides of a table, the outcome of flipping one does not determine the outcome of flipping the other, unless someone secretly glued them together, and even then the glue would be local. Philosophers of physics have examined this assumption carefully. Howard Stein, for example, analyzed separability as a foundational principle in classical field theories. In separable theories, the state of a composite system is fully determined by the states of its parts and their spatial relations. Nothing more is required. No hidden global structure binds them beyond what is specified locally. In other words, the whole is nothing over and above the sum of its parts. This way of thinking shaped not only physics but intuition itself. It aligns with daily experience. Chairs are chairs whether or not someone is sitting on them. The moon does not borrow its identity from Mars. Objects exist independently and interact when forces act between them. Even when gravity stretches across astronomical distances, the interaction can be described in terms of local fields or geometric curvature of spacetime, as Einstein later proposed in general relativity in 1915. Mass and energy curve spacetime locally, and objects follow that curvature. No mysterious thread connects distant bodies. The geometry is continuous, and causal influence still respects the speed of light. So the picture is coherent, it is mathematically precise, it is experimentally verified across scales from falling apples to orbiting galaxies, and yet, in the early decades of the 20th century, as quantum mechanics took shape through the work of Max Planck, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, something unexpected emerged. The mathematical formalism allowed for states of composite systems that could not be written as independent states of their parts. Two particles could be described by a single joint wave function that resisted factorization. Their properties were not merely correlated in a classical sense, they were defined only in relation to one another. This was not an issue of signals travelling too quickly. It was not about sending information faster than light. It was deeper than that. It suggested that separability itself might fail. Imagine two particles created together in a carefully prepared process. According to quantum theory, their combined state can encode correlations so strong that measuring one immediately constrains the possible outcomes of measuring the other, even if they are separated by kilometers. Even if they are separated by continents. Importantly, nothing observable travels between them at the moment of measurement. There is no detectable pulse, no hidden flash racing through space. Each measurement result taken alone appears random. Only when the results are later compared do the correlations reveal themselves. The guiding question is not whether information is transmitted. It is more subtle. How can correlated behavior persist across space without interaction? In classical physics, correlations arise from common causes in the past. If two clocks are set together and then separated, they may tick in synchrony for a while. If two gloves are placed in separate boxes, opening one box and finding a left glove instantly tells someone that the other box contains a right glove. But in those cases the properties were already fixed. Quantum entanglement appears to resist that explanation. The outcomes are not determined in advance by local hidden variables, at least not in any way consistent with both locality and experimental evidence. This tension would later be made precise by John Bell in the 1960s, but even before that the seeds of unease were visible. What quantum mechanics introduced was not simply randomness. It introduced a new structure of physical description. The quantum state of a composite system cannot always be decomposed into independent states of its constituents. The mathematics of tensor products and superposition permits inseparable combinations. This is why entanglement is better described as a structural challenge rather than a communication puzzle. The puzzle is not how something travels from one particle to another. The puzzle is why the formal description of the pair refuses to split cleanly into two separate descriptions. In classical mechanics, if the state of system A is known and the state of system B is known, then the state of the combined system is simply the pair of those two states. There is no extra layer. In quantum mechanics, that simplicity dissolves. The combined state may contain relational information that is not reducible to the individual subsystems. This departure from classical independence does not immediately overthrow relativity. The speed limit remains intact. The no-signaling principle ensures that no controllable information can be sent faster than light. But the conceptual terrain shifts. The assumption that the world is fundamentally built from independent parts becomes less secure. The comfortable image of isolated objects, each carrying its own definite properties, begins to soften. What replaces it is not chaos, and not mysticism, but a more intricate architecture, one in which relationships can be primary, one in which the whole sometimes contains more structure than the sum of its parts. And it is from this shift that quantum entanglement emerges, not as an exotic exception, but as a natural consequence of how quantum theory describes reality. This stage is now set. Classical separability and locality stand firm in their domains, tested and trusted. Yet within the quantum framework, a different pattern quietly takes shape, inviting a careful and patient exploration of how distant things can remain, in some profound sense, connected. At the turn of the 20th century, physics appeared almost complete. Classical mechanics described motion. Thermodynamics governed heat. Maxwell's equations unified electricity, magnetism, and light. The remaining problems seemed technical, like small wrinkles waiting to be ironed flat. One of those wrinkles involved blackbody radiation, the glow emitted by hot objects. Experiments showed that heated objects radiate energy in a very specific distribution across frequencies. Classical physics predicted something dramatic and incorrect. According to classical equipartition, energy should pile up at high frequencies without limit, leading to what later became known as the ultraviolet catastrophe. Nature, however, refused to cooperate. In 1900, Max Planck proposed something radical, though he initially viewed it as a mathematical convenience. He suggested that energy exchange between matter and radiation occurs in discrete packets. Instead of energy flowing continuously, it is emitted or absorbed in units proportional to frequency. The proportionality constant, now called Planck's constant, is extraordinarily small, roughly 6.6 times 10 to the minus 34 joule seconds. It is so tiny that its effects are invisible in everyday life, yet at microscopic scales it governs everything. Planck did not immediately interpret quantization as a statement about reality itself. That step came in 1905, when Albert Einstein used the idea to explain the photoelectric effect. Light, he argued, sometimes behaves as if it consists of discrete quanta, later called photons. These quanta transfer energy in indivisible amounts. The energy of each quantum is determined by frequency, not intensity. Increase the intensity and you increase the number of quanta, not the energy per quantum. This was the beginning of a structural shift. Energy was no longer an infinitely divisible fluid. Nature appeared granular at a fundamental level. As the 1920s unfolded, the mathematical formalism of quantum mechanics took shape. Werner Heisenberg introduced matrix mechanics in 1925. Erwin Schrödinger developed wave mechanics in 1926. Their approaches looked different, but they proved mathematically equivalent. Pascal Jordan, often mentioned less frequently than his contemporaries, played a crucial role in formalizing quantization procedures and advancing what became quantum field theory. Jordan helped clarify how classical variables could be promoted to operators that obey non-classical commutation relations. One of the central relations introduced in this period was the canonical commutation relation between position and momentum. In words, it can be expressed as position multiplied by momentum minus momentum multiplied by position equals the imaginary unit multiplied by Planck's constant divided by 2pi. This non-commutativity has no analogue in classical mechanics. It encodes the Heisenberg uncertainty principle directly into the structure of the theory. But it was John von Neumann who provided the rigorous mathematical foundation. In 1932, he formulated quantum mechanics within the framework of Hilbert space, an abstract vector space equipped with an inner product. In this formulation, a physical system is described by a state vector in Hilbert space. Observables, such as position or spin, are represented by self-adjoint operators acting on that space. This may sound abstract, and it is, but the shift is profound. A quantum state is not a list of definite properties like position and velocity. Instead, it is a vector encoding the probabilities of different measurement outcomes. Superposition arises naturally in this framework. If one state is allowed and another state is allowed, then any linear combination of those states is also allowed. This is not a philosophical statement. It is a direct mathematical consequence of the vector space structure. Consider a particle that can be measured in one of two possible spin orientations along a chosen axis. In classical thinking, it must already possess one orientation or the other. In quantum mechanics, the state can be a superposition of both possibilities. The state vector contains complex probability amplitudes, not classical probabilities. Max Born provided the rule that connects these amplitudes to experiment. According to the Born rule, the probability of obtaining a particular outcome is given by the square of the magnitude of the corresponding amplitude. In words, probability equals amplitude multiplied by amplitude conjugate. This simple prescription has been confirmed by countless experiments, from electron diffraction to atomic spectroscopy. The important detail is that the amplitude itself can interfere. When two possible paths contribute to a single outcome, their amplitudes add before probabilities are calculated. This leads to interference patterns, such as those observed in the double-slit experiment. Individual particles, fired one at a time, accumulate into a pattern characteristic of waves. Already, the picture of intrinsic properties begins to loosen. The quantum state does not assign a definite trajectory to a particle between measurements. It encodes a structured set of possibilities, weighted by amplitudes. More significantly, when multiple systems are considered together, the structure becomes richer still. In classical physics, the state of a composite system is just the collection of its parts. If system A has state A and system B has state B, then the combined system has state A and B. Nothing extra appears. In the Hilbert space formalism, the combined system is described by the tensor product of the individual Hilbert spaces. This mathematical construction allows for states that cannot be written as a simple product of two independent vectors. These are entangled states. They contain relational information that does not reduce to properties of the parts. This is where the structural revolution becomes unmistakable. The quantum state of a composite system can encode correlations that are not attributable to hidden local properties assigned independently to each subsystem. Philosophers of science have taken notice. James Ladyman, among others, has argued for a position known as structural realism. Structural realism suggests that what science reveals most reliably is not the intrinsic nature of objects, but the structure of relations between them. According to this view, the enduring content of physical theory lies in its mathematical structure, particularly the relational patterns captured by its formalism. Quantum mechanics seems to support this perspective. The state vector does not describe little billiard balls with secret labels. It describes a network of potential measurement outcomes and their interrelations. When systems become entangled, the relational structure becomes primary. This does not mean that objects cease to exist. Rather, it suggests that their properties are not always independent of one another. The whole can possess structure that is not decomposable into separate self-contained pieces. Von Neumann's formalism makes this explicit. The state of a composite system is a single vector in a larger Hilbert space. If that vector cannot be factorized into separate vectors for each subsystem, then the systems are entangled. The mathematics does not treat this as exotic. It treats it as a natural possibility. In fact, interaction between systems tends to produce entanglement generically. When two quantum systems interact through any non-trivial coupling, their joint state typically becomes inseparable. Avoiding entanglement requires special conditions. In this sense, separability is the exception, not the rule. This is a reversal of classical intuition. In the classical worldview, independence is assumed unless forces act. In quantum theory, interaction often leaves behind enduring relational structure even after systems separate in space. The structural shift, then, is not merely about discreteness or uncertainty. It is about how physical description is organized. Quantum states encode possibilities and relations rather than fixed intrinsic properties. Superposition reflects the linear structure of Hilbert space. The Born rule connects amplitudes to probabilities. Tensor products allow composite systems to exhibit inseparable structure. None of this violates relativity. The speed of light remains a causal limit. No equation within standard quantum mechanics permits controllable signals to exceed that boundary. But the independence of distant systems can no longer be taken for granted. The revolution is quiet but deep. It does not shout. It rearranges the foundation. Instead of a universe built from independent blocks that occasionally interact, quantum theory presents a world where relations are woven into the mathematical fabric from the start. In that fabric, the idea of complete classical separability begins to look less like a universal truth and more like a useful approximation that works beautifully at large scales. And within that refined structure, the phenomenon called entanglement emerges naturally, not as an anomaly, but as an expression of how quantum states are fundamentally constructed. In 1935, Erwin Schrödinger wrote a paper in response to a challenge raised by Albert Einstein, Boris Podolsky, and Nathan Rosen. Schrödinger did not treat their argument as a minor technical puzzle. He identified something deeper. He gave it a name: entanglement. Schrödinger described entanglement as the characteristic trait of quantum mechanics, the feature that forces the theory to depart most radically from classical lines of thought. He did not regard it as an accidental curiosity. In his words, it was not one but the defining feature of quantum theory. To understand why, it helps to recall how composite systems are described mathematically. In quantum mechanics, each system is represented by a state vector in a Hilbert space. When two systems are combined, their joint description lives in the tensor product of their individual Hilbert spaces. That tensor product construction allows for states that cannot be written as a simple product of one state for the first system and another state for the second. If the joint state can be written as a product, then the systems are separable. Each has its own independent description, but if the joint state cannot be factorized in that way, then the systems are entangled. Their state is non-factorizable. The total description contains correlations that are not reducible to properties assigned individually. This definition is precise and structural. It does not rely on distance, measurement, or signaling. It is about the form of the state itself. Schrödinger realized that once two systems interact and become entangled, even if they later move far apart, their joint state may remain inseparable. The mathematics does not automatically restore independence when spatial separation increases. Distance does not factorize the tensor product. At roughly the same time, Einstein, Podolsky, and Rosen published what became known as the EPR paper. Their goal was to show that quantum mechanics, as formulated at the time, was incomplete. The EPR argument considered two particles that interact and then separate. By carefully choosing what observable to measure on the first particle, an experimenter could predict with certainty the result of measuring a corresponding observable on the second particle. If the first measurement revealed position, the position of the second could be inferred. If the first revealed momentum, the momentum of the second could be predicted. Einstein and his colleagues introduced a criterion of reality. They proposed that if one can predict with certainty the value of a physical quantity without disturbing a system, then there must exist an element of physical reality corresponding to that quantity. From this premise, they concluded that the second particle must possess definite values for both position and momentum, even though quantum mechanics does not assign simultaneous definite values to both. Therefore, they argued the quantum description must be incomplete. There must be hidden variables specifying those values. Einstein's discomfort was not primarily about randomness. It was about separability and locality. He believed in what is sometimes called the separability principle, that spatially separated systems have their own independent real states. In correspondence with Max Born, Einstein repeatedly emphasized that the real state of one system should not depend on what is done to another distant system. In a letter written in the 1940s, Einstein expressed his concern that quantum mechanics allows what he called telepathic correlations. He did not mean this literally. He meant that the formalism appeared to permit instantaneous influence at a distance, something incompatible with his relativistic understanding of spacetime. It is important to distinguish two ideas that are often blended together: realism and determinism. Determinism is the view that the present state of the universe fixes the future uniquely. Classical mechanics is deterministic in this sense. Given initial conditions and forces, future trajectories are determined. Realism, in the context of the EPR debate, is the belief that physical systems possess definite properties independent of observation. A realist may accept indeterminism and still hold that properties exist whether or not they are measured. Einstein's objection was not simply that quantum mechanics was indeterministic. He could have accepted probabilistic laws if they still described underlying real states. His deeper concern was that quantum mechanics seemed to deny independent reality to spatially separated systems. Schrödinger's response was subtle. Rather than dismissing entanglement as a flaw, he embraced it as an unavoidable feature of the theory. He recognized that when two systems interact, they typically become entangled, and that this entanglement persists even after they separate. The joint state remains a single mathematical object. To illustrate, consider a simplified example involving spin. Suppose two particles are prepared in a state where their total spin is zero. This means that if one particle is measured to have spin up along a chosen axis, the other will be found to have spin down along that same axis. Before measurement, neither particle is assigned a definite spin in that direction. The joint state encodes perfect anti-correlation. Mathematically, this state cannot be written as one particle being spin up times the other being spin down, plus something else assigned independently. The description is holistic. The correlation is built into the structure of the state vector. When one particle is measured, the joint state is updated according to the rules of quantum mechanics. The measurement outcome appears random locally, yet the correlation with the distant particle is exact. This is not because a signal has raced across space. It is because the joint state never factorized in the first place. Schrödinger saw that entanglement challenges classical intuitions about individuality. In classical physics, if two objects are separated by a large distance, they are simply two objects. In quantum mechanics, they may still share a single inseparable state. This inseparability is not an add-on. It follows directly from the linear structure of Hilbert space and the tensor product construction for composite systems. If superposition is allowed for single systems, and tensor products are used to combine systems, then entangled states are mathematically inevitable. Avoiding entanglement would require rewriting the formalism entirely. In this sense, entanglement is not peripheral. It is woven into the core architecture of quantum mechanics. Every interaction that couples two systems has the potential to produce entanglement. In practice, microscopic systems are almost always entangled with their environments. Decoherence theory, developed decades later by H. Dieter Zeh and Wojciech Zurek, would show how this pervasive entanglement leads to the appearance of classical definiteness at large scales. But in 1935, the implications were still unfolding. Einstein regarded entanglement as evidence that the theory was incomplete. Schrodinger regarded it as evidence that the world itself might not conform to classical separability. The disagreement was not about experimental data at that time. It was about interpretation and structure. Does the mathematical formalism describe an underlying reality that is separable and local, supplemented by hidden variables? Or does it reveal that separability is not fundamental? The question lingered for decades until John Bell showed that no theory preserving both locality and certain forms of realism could reproduce all the predictions of quantum mechanics. But even before Bell's theorem, the seeds of that conclusion were visible in Schrödinger's recognition of entanglement as central. What began as a philosophical concern became a defining feature of the theory. Entanglement is not a loophole. It is not an experimental glitch. It is a structural property of quantum states. When systems interact, they form a joint description that may resist decomposition into independent parts. Spatial separation does not automatically dissolve that joint structure. The classical intuition that the whole is always just the sum of its parts turns out to be, at best, an approximation valid at certain scales. At the quantum level, the relations encoded in the joint state can be more fundamental than the individual properties of the parts themselves. And once that possibility is acknowledged, the idea that distant things can remain connected ceases to be a mystery about signals, and becomes instead a statement about how nature organizes its deepest descriptions. For several decades after the Einstein-Podolsky-Rosen paper, the debate over quantum entanglement remained largely philosophical. Einstein suspected that hidden variables might restore a deeper, separable description of reality. Schrödinger accepted entanglement as fundamental, yet no clear experimental path existed to decide between them. That changed in 1964, when John Bell published a short but revolutionary paper. Bell was working at the European Organization for Nuclear Research, known as CERN. His insight was precise and mathematical. He asked a simple question. If the world obeys both locality and realism in the EPR sense, what observable constraints would follow? Local realism combines two assumptions. Locality means that events occurring at one location cannot instantaneously influence distant events. Realism means that physical properties have definite values prior to measurement. Bell showed that any theory satisfying both conditions must obey certain statistical inequalities. These inequalities set limits on the strength of correlations that can be observed between measurements performed on spatially separated systems. Bell's original formulation involved pairs of particles measured along different orientations. If hidden variables predetermined the outcomes, and if no faster-than-light influence occurred between measurement events, then the correlations between results would satisfy a specific bound. Quantum mechanics predicts violations of that bound. The power of Bell's theorem lies in its generality. It does not depend on the detailed mechanics of any particular hidden variable theory. It applies to all local hidden variable models. Bell demonstrated that the predictions of quantum mechanics are incompatible with the joint assumptions of locality and realism. The argument is statistical. It concerns correlations measured across many trials, not individual events. Suppose two observers, often called Alice and Bob in modern discussions, measure properties of entangled particles at distant locations. Each can choose between different measurement settings. Under local realism, the results at each location depend only on the local setting and on shared hidden variables established when the particles were created. From this framework, one can derive an inequality restricting the possible correlations. Bell showed that quantum mechanics predicts stronger correlations than this inequality allows. The original inequality was later reformulated into a more experimentally accessible version in 1969 by John Clauser, Michael Horn, Abner Shimony, and Richard Holt. This became known as the Clauser-Horn-Shimony-Holt inequality, often abbreviated in textbooks. The reformulation simplified the statistical analysis and clarified how to test Bell's predictions in the laboratory. The Clauser-Horn-Shimony-Holt inequality sets an upper limit on a particular combination of correlation measurements. In words, one can say that under local realism, the magnitude of this combination cannot exceed 2. That number is not arbitrary. It follows directly from the algebra of predetermined outcomes, bounded between -1 and +1. Quantum mechanics predicts that this same combination can reach a value of 2 times the square root of 2. That is approximately 2.828. This maximum quantum value is known as Cyrulson's bound, named after Boris Cyrulson, who derived it in 1980. Cyrulson's contribution is subtle and important. Quantum mechanics violates the classical bound of 2, but it does not allow correlations to become arbitrarily strong. The theory imposes its own upper limit. Even though quantum correlations exceed classical expectations, they remain constrained by the structure of Hilbert space. In other words, quantum mechanics is more correlated than classical physics, but not maximally correlated in every conceivable way. To see why this matters, consider that one could imagine hypothetical theories that allow even stronger correlations while still respecting the no-signaling principle. Such theoretical constructs are sometimes called Popescu-Rohrlich boxes, after Sandu Popescu and Daniel Rohrlich. These would achieve the algebraic maximum value of 4 for the same correlation expression, while still preventing faster-than-light communication. Nature, however, does not reach that extreme. Experimental measurements consistently approach Cyrulson's bound but never exceed it. This suggests that quantum mechanics occupies a precise middle ground between classical local realism and unrestricted non-local correlation. Another important development came from Arthur Fine in 1982. Fine's theorem established that the existence of a joint probability distribution for all measurement outcomes is equivalent to the satisfaction of Bell-type inequalities. In simpler terms, if one can assign consistent predetermined values to all possible measurements simultaneously, then the Bell inequalities must hold. If the inequalities are violated, no such joint assignment is possible. Fine's results sharpened the conceptual picture. Violating Bell inequalities is not merely a technical quirk. It means that no underlying local hidden variable model can reproduce the observed correlations. This forces a choice. Either locality must be abandoned in some sense, or realism as defined in the EPR framework must be revised, or one must accept that the joint assumptions cannot be maintained simultaneously. It is important to clarify what is meant here by abandoning locality. Bell himself was careful. The no-signaling theorem still holds in quantum mechanics. Measurement outcomes at one location cannot be used to transmit controllable information to another location faster than light. Relativistic causality remains intact at the operational level. The tension arises at the level of underlying explanation. If one insists on realism in the sense that properties exist independently of observation, then those properties cannot be purely local. The correlations imply some form of non-local dependence within the underlying model. Alternatively, one may reinterpret realism itself. Some interpretations, such as relational quantum mechanics or cubism, treat measurement outcomes as relational or agent-dependent rather than as revealing pre-existing local properties. What Bell's theorem accomplishes is remarkable. It transforms a philosophical dispute into an experimentally testable question. It moves the conversation from speculation to measurement, and the measurements have been performed repeatedly. Beginning with the experiments of Alain Aspect in the early 1980s, and continuing through increasingly refined tests in Europe, North America, and Asia, Bell inequality violations have been observed under conditions designed to eliminate alternative explanations. The numbers matter here. In well-designed experiments using entangled photons, the measured correlation values approach 2.7 or higher, close to the quantum mechanical maximum of approximately 2.828. Classical local hidden variable theories would restrict that value to 2 or below. These results are not statistical flukes. They are reproduced across laboratories, technologies, and decades. Yet even within this stronger correlation regime, quantum mechanics remains bounded. Zerelson's bound defines the ceiling. The structure of Hilbert space and the Born rule together constrain how large the correlations can become. This boundedness is a clue. It suggests that quantum theory is not merely a random violation of classical limits. It is a consistent and mathematically coherent framework with its own internal geometry. The limits of local realism are therefore precise. Classical local hidden variable theories impose one boundary. Hypothetical superquantum theories would allow more extreme correlations. Quantum mechanics sits exactly between them, exceeding classical limits, but stopping short of logical extremes. Bell's theorem thus establishes two key facts. First, the world does not conform to local realism in the EPR sense. Second, the non-classical correlations observed in nature are structured and limited, not arbitrary. Entanglement is not an unbounded breakdown of order. It is a disciplined departure from classical separability, governed by the mathematical architecture of quantum theory. And with that, the question of how distant things can remain connected moves from philosophical unease to empirical reality. The correlations are stronger than any classical model allows, yet precisely as strong as quantum mechanics predicts. By the late 1970s, Bell's theorem had transformed a philosophical debate into an experimental challenge. The inequalities were clear. Quantum mechanics predicted their violation. Local hidden variable theories required that they hold. What remained was the delicate task of testing them in the real world, where detectors are imperfect, signals travel through cables, and nature does not always cooperate politely. In the early 1980s, Alain Aspect and his team at the Institut d'Optique near Paris carried out a series of experiments that would become historic. They produced pairs of entangled photons using atomic cascades in calcium atoms. When an excited atom decayed in 2 steps, it emitted 2 photons whose polarizations were correlated in precisely the way quantum mechanics described. The key innovation in Aspect's experiment, reported in 1982, was the rapid switching of measurement settings while the photons were already in flight. The measurement orientation on one side could be changed faster than light could travel from one detector to the other. This design aimed to address what became known as the locality loophole. If the settings were chosen quickly and independently, then no slower than light signal could coordinate the outcomes between the two stations. The results violated the Clauser-Horn-Schimmeny-Holt inequality. The measured correlation values exceeded the classical limit of 2 and approached the quantum mechanical prediction. These experiments did not eliminate every possible alternative explanation, but they provided strong evidence that nature behaves in accordance with quantum theory rather than local realism. From there, experimental techniques improved steadily. In the 1990s and early 2000s, Anton Zeilinger and his collaborators in Vienna advanced photon entanglement experiments dramatically. Using spontaneous parametric down conversion in nonlinear crystals, they generated highly entangled photon pairs with improved efficiency and control. Spontaneous parametric down conversion is a process in which a single high-energy photon entering a crystal splits into two lower-energy photons whose polarizations are entangled. Zeilinger's group demonstrated long-distance entanglement distribution, sending entangled photons across kilometers of optical fiber and even across free space between islands in the Canary Archipelago. These experiments showed that entanglement survives not just in carefully shielded laboratory setups, but across significant real-world distances. Yet two major concerns remained in Bell tests. The first was the locality loophole, already addressed partially by rapid switching of measurement settings. The second was the detection loophole. In many early experiments, only a fraction of emitted photons were successfully detected. If the subset that was detected was not representative of the whole, then hidden variable explanations might still survive by exploiting this sampling bias. To close the detection loophole, experiments required very high detection efficiencies. In practice, this meant using systems other than photons, or dramatically improving photon detectors. A major milestone arrived in 2015, when Ronald Hansen and his team at Delft University of Technology reported what was widely described as the first loophole-free Bell test. Their experiment used entangled electron spins in diamond, specifically nitrogen vacancy centers embedded in diamond crystals. These solid-state systems allowed for high detection efficiencies and spatial separation of measurement stations. The Delft experiment separated the two measurement locations by over 1 kilometer and ensured that the choice of measurement setting and the detection event at each location were space-like separated. This means that no signal travelling at or below the speed of light could link the relevant events in time. Both the locality and detection loopholes were addressed simultaneously. The observed correlations violated the Bell inequality with statistical significance, aligning with quantum mechanical predictions. Around the same time, independent experiments were conducted by groups at the National Institute of Standards and Technology in the United States and by teams in Austria. The National Institute of Standards and Technology experiment used entangled photons with highly efficient superconducting detectors, achieving detection efficiencies sufficient to close the detection loophole. The Austrian group employed entangled photon pairs with carefully timed random setting choices to ensure locality conditions. The convergence of these independent efforts was striking. Different physical systems, different laboratories, different technologies, yet the same outcome. The measured correlations consistently exceeded the classical limit while remaining within Serelson's bound predicted by quantum mechanics. It is worth pausing on what closing a loophole means in this context. A loophole is not a mistake in arithmetic. It is a potential alternative explanation consistent with both the data and a classical hidden variable model. If detectors miss too many events, one might argue that the detected sample is biased. If measurement settings are chosen too slowly or in a correlated way, one might argue that information could travel between the stations before measurements are completed. Closing a loophole means designing the experiment so that these alternative explanations are no longer plausible under reasonable physical assumptions. Of course, one can always imagine increasingly exotic possibilities, such as superdeterminism, in which hidden variables conspire to correlate measurement settings and outcomes in advance. But such proposals require abandoning widely accepted assumptions about statistical independence and free choice in experimental design. For practical purposes, the experimental community now regards Bell inequality violations as firmly established empirical facts. In addition to laboratory experiments, entanglement has been demonstrated over even larger scales. In 2017, the Chinese Messius satellite, led by Jianwei Pan and colleagues, distributed entangled photons between ground stations separated by more than 1,000 kilometers. These experiments confirm that entanglement persists across distances comparable to the size of a small country. Throughout these decades of testing, one pattern remains constant. Whenever measurement settings are chosen independently, and detection efficiencies are sufficiently high, the observed correlations match the predictions of quantum mechanics. They exceed classical bounds but never surpass the quantum limit. The numbers themselves tell a calm and steady story. The Clauser-Horn-Shimony-Holt parameter consistently rises above 2, often reaching values near 2.7 or slightly higher, depending on experimental conditions. It never drops neatly back into the classical regime when the apparatus is functioning correctly. This is not a fragile anomaly. It is a robust feature of the world. The elegance of Bell's theorem lies in its clarity. The power of the experiments lies in their consistency. Together, they reveal that entanglement is not a philosophical curiosity. It is an experimentally confirmed property of nature. Distant systems, when prepared in certain joint quantum states, display correlations that no local hidden variable theory can reproduce. And yet, despite this non-classical behavior, no faster-than-light signals are observed. No breakdown of relativistic causality appears. Instead, what emerges is a refined understanding. The structure of quantum states encodes relational information that classical models cannot capture. The empirical confirmation is now woven into the fabric of modern physics, from optical tables in Paris to diamond laboratories in Delft, from precision instruments at the National Institute of Standards and Technology to satellites orbiting high above the Earth. The verdict has been remarkably consistent. Nature, when asked carefully and repeatedly, answers in favour of quantum entanglement. By this point, the picture might feel slightly unsettling. Correlation stronger than classical physics allows. Measurement outcomes linked across space. Bell inequalities violated. It would be natural to wonder whether something truly dramatic is happening behind the scenes. Perhaps a hidden signal darts between particles faster than light. Perhaps relativity has quietly been overruled. It has not. One of the most important results in modern quantum theory is known as the no-signaling theorem. It states, with mathematical clarity, that quantum mechanics does not allow controllable information to be transmitted faster than light, even when systems are entangled. This theorem is not an added patch or a philosophical reassurance. It follows directly from the structure of quantum states and the Born rule. To see why, consider again two observers measuring entangled particles at distant locations. Each observer can choose between different measurement settings. The joint state of the pair encodes correlations that will become visible when results are later compared. However, when one observer performs a measurement, the local statistics at the other location remain unchanged. No matter what choice of measurement is made here, the probability distribution observed there is exactly the same. The outcomes at each location are individually random. This is the key. Entanglement produces correlations, but it does not produce controllable outcomes. If an observer on one side tries to encode a message by choosing one measurement setting or another, the distant observer will not see any change in the pattern of local results. Only when the two sets of results are brought together and compared through ordinary classical communication do the correlations reveal themselves, and that classical communication is limited by the speed of light. Mathematically, the reason lies in how quantum probabilities are calculated. Suppose two systems are described by a joint density matrix. To determine the statistics accessible to one subsystem alone, one performs what is called a partial trace over the other subsystem. This operation produces a reduced density matrix that describes local measurement probabilities. The crucial point is that local operations performed on one subsystem do not alter the reduced density matrix of the distant subsystem in a way that depends on the choice of measurement. The formal expression can be stated clearly. The probability of outcome B equals the trace of the reduced density matrix of B multiplied by the measurement operator for B. That reduced density matrix does not depend on which measurement was chosen at the distant location. This independence is built into the linearity of quantum mechanics. If this were not the case, entanglement would permit instantaneous communication. One could simply choose measurement settings to send binary signals across arbitrary distances. The universe would then allow faster-than-light signaling, contradicting Einstein's special relativity, which states that no information-carrying influence travels faster than light in vacuum. Special relativity, introduced in 1905, rests on two postulates. First, the laws of physics are the same in all inertial frames. Second, the speed of light in vacuum is invariant and sets a universal speed limit. Countless experiments, from particle accelerators to satellite timing systems, confirm this structure. Global positioning system satellites must account for relativistic time dilation to maintain accuracy within meters. Quantum mechanics respects this limit. The correlations predicted by quantum theory are sometimes described as non-local. That term can be misleading if interpreted as faster-than-light causation. What Bell's theorem demonstrates is that no local hidden variable model can reproduce the correlations. It does not demonstrate that signals propagate superluminally. There is a difference between influence and correlation. In classical physics, correlations can arise from common causes in the past. If two dice are prepared with matching faces and then separated, the correlation reflects a shared origin. In quantum mechanics, the situation is more subtle. The shared origin establishes an entangled joint state, and the correlations are revealed upon measurement. But the act of measurement on one side does not transmit a usable influence to the other side. The no-signaling theorem ensures that relativistic causality remains intact. This compatibility is not accidental. Quantum field theory, the framework that combines quantum mechanics with special relativity, is constructed to preserve locality at the level of field commutation relations. Observables associated with space-like separated regions commute. In words, measurements performed in one region do not disturb measurements in another region, when those regions are separated by more distance than light could traverse during the interval between them. This commutation property is essential for maintaining relativistic consistency. Yet even with this structure in place, the correlations remain stronger than classical physics permits. They exceed the bound of two established by the Clauser-Horn-Schiemany-Holt inequality, reaching up to approximately 2.828, Cyrillson's bound. So the universe threads a careful line. On one side, classical local realism predicts weaker correlations. On the other, hypothetical super-quantum theories could produce even stronger correlations while still avoiding signaling. Quantum mechanics occupies a precise middle ground. It allows correlations that challenge classical separability, yet it enforces limits that preserve causal structure. This balance is remarkable. It suggests that entanglement is not an uncontrolled loophole in physical law. It is a structured feature emerging from the geometry of Hilbert's space and the probabilistic interpretation provided by Max Born. One might imagine entanglement as a connection that spans space, but it's more accurate to describe it as a property of the joint state established when the systems interacted. The connection does not travel. It does not propagate. It is simply there, encoded in the mathematics. When measurements occur, the joint probabilities reflect that encoding. The results align in ways that cannot be explained by local hidden variables. Yet no observer can exploit the alignment to send messages faster than light. In this sense, quantum mechanics reshapes the notion of locality without dismantling relativity. The independence of distant systems at the level of hidden variables cannot be maintained, but the independence of local measurement statistics remains intact. This distinction is subtle but essential. Relativistic causality governs what can be used to transmit information and influence events. Quantum entanglement governs how joint probabilities are structured across space. The two frameworks coexist without contradiction, and once this is understood, the focus shifts. If entanglement does not allow faster-than-light signaling, then its significance must lie elsewhere. Not in breaking speed limits, but in revealing something about how properties are defined and how measurement contexts matter. The deeper implications are not about communication. They concern the structure of physical description itself, the way outcomes depend on measurement settings, the way correlations emerge from non-factorizable states. The absence of faster-than-light signaling closes one dramatic possibility, but it opens a more intriguing one. If distant systems cannot signal instantaneously, yet cannot be described independently either, then the classical picture of intrinsic local properties may need revision. And that leads toward an even more refined question, not merely whether the world is local, but whether properties themselves are contextual. Entanglement challenges the idea that distant systems can always be described independently. Contextuality goes even further. It questions whether a single system can be described independently of how it is measured. In 1967, Simon Kochen and Ernst Specker published a theorem that would quietly deepen the foundations of quantum mechanics. The Kochen-Specker theorem addresses a different assumption from Bell's theorem. Bell focused on locality combined with realism. Kochen and Specker focused on non-contextual realism. Non-contextuality is the idea that the value of a measurable quantity is independent of which other compatible measurements are performed alongside it. In classical physics, this seems obvious. If a book has a mass of 1 kilogram, that mass does not depend on whether one also measures its temperature or its width. The property is assumed to exist with a definite value, regardless of experimental arrangement. Quantum mechanics does not permit this assumption in general. The Kochen-Specker theorem demonstrates that in Hilbert spaces of dimension 3 or greater, it is impossible to assign definite values to all quantum observables in a way that preserves consistency with the functional relationships between them, while also keeping those assignments independent of measurement context. That statement sounds technical, but the underlying idea is accessible. Suppose one tries to imagine that every observable property of a quantum system has a pre-existing value, even if unknown. Furthermore, suppose that this value does not depend on which other commuting observables are measured at the same time. Kochen and Specker showed that this attempt leads to contradictions. The structure of quantum observables is such that certain sets of measurements are mutually compatible, meaning they can be measured together. However, the same observable may appear in different compatible sets. If one tries to assign fixed values that satisfy all these overlapping relationships simultaneously, one eventually reaches an inconsistency. In simple terms, the value of a quantum observable cannot be thought of as an intrinsic label attached to the system alone. It depends on the measurement context. It is important to distinguish contextuality from non-locality. Non-locality concerns correlations between spatially separated systems, as highlighted by Bell's theorem. Contextuality can arise even for a single system, without any spatial separation at all. It is a statement about how measurement outcomes depend on the structure of the measurement setup. A helpful conceptual aid comes from Robert Speckens and his toy model, introduced in 2007. Speckens constructed a simplified model that reproduces many features of quantum behavior, including certain types of interference and epistemic restrictions, while remaining fundamentally classical in structure. In Speckens' toy theory, systems possess underlying states, but observers have limited knowledge about them. This knowledge restriction produces behaviors that resemble quantum phenomena. However, the model remains non-contextual. It cannot reproduce the full range of contextuality exhibited by quantum mechanics. The failure of the toy model to capture contextuality highlights how deeply non-classical this feature is. Contextuality is not simply about limited information. It is about the structural relationships between observables encoded in Hilbert space. To understand why contextuality matters, consider a quantum system with spin 1. Measurements of spin along different directions correspond to operators that share certain mathematical relationships. The Kochen-Specker theorem shows that there is no assignment of definite spin values along all directions that respects those relationships without depending on which other measurements are jointly performed. This means that quantum observables do not carry context-independent values in the way classical properties do. Contextuality therefore extends the challenge to classical realism beyond spatial considerations. Even without entanglement, even within a single particle, the classical picture of intrinsic properties falters. This feature has practical consequences as well. In recent years, researchers have identified contextuality as a potential resource for quantum computational advantage. Certain models of quantum computation, such as measurement-based quantum computing, rely on specific forms of contextuality to achieve tasks that appear intractable for classical systems. Theoretical work by researchers including Robert Rausendorf has linked contextuality to the power of quantum computation. In particular, contextuality has been shown to be necessary for achieving universal quantum computation in some frameworks. The intuition is that contextuality reflects a richer logical structure than classical Boolean logic allows. Classical bits obey straightforward truth tables. Quantum systems, constrained by contextual relationships, permit patterns of correlation that cannot be simulated efficiently by non-contextual hidden variable models. This does not mean that contextuality alone guarantees computational speedup, but it appears to be one of the non-classical ingredients that distinguish quantum information processing from classical computation. Seen from this perspective, contextuality is not merely a philosophical curiosity. It is a structural feature of quantum theory with operational consequences. It also clarifies that the departure from classical thinking is not limited to spatial separation. Even if one were to confine attention to a single laboratory bench, examining a single trapped ion or superconducting qubit, contextuality would still emerge from the algebra of observables. The classical worldview assumes that properties exist independently of measurement and independently of one another. Quantum mechanics replaces that picture with a framework in which measurement outcomes are tied to the structure of the entire experimental arrangement. This does not imply that measurement creates reality from nothing. It implies that the properties revealed are relational within a specific context. The Cauchy-Specker theorem makes this precise. It is not about faster-than-light influence. It is about the impossibility of embedding quantum observables into a single global assignment of pre-existing values that ignore context. Combined with Bell's theorem, contextuality strengthens the conclusion that quantum mechanics cannot be reduced to a classical model with hidden local properties. Entanglement shows that spatially separated systems can share inseparable structure. Contextuality shows that even locally, properties resist classical assignment. The shift becomes clearer. The classical assumption that the world is composed of independently existing properties, merely waiting to be revealed, gives way to a subtler picture. Observables are defined within a network of compatible measurements. Outcomes depend not just on the system, but on how the question is asked. And yet this departure remains disciplined. The mathematical framework of Hilbert space, operator algebra, and the Born rule governs the structure consistently. The theory does not dissolve into ambiguity. It replaces classical independence with structured relational constraints. In that quiet replacement, the meaning of measurement becomes more intricate, not mysterious in a supernatural sense, but structurally interwoven with the questions posed. The deeper pattern emerging is that the classical ideal of intrinsic context-free properties is not fundamental at the quantum level. What remains fundamental are the relations encoded in the formalism and the probabilistic rules that connect them to experiment. And that structural insight prepares the ground for understanding how classical reality itself may emerge from a theory that, at its core, refuses to grant properties independent of context. If entanglement and contextuality are so fundamental, a natural question arises. Why does the everyday world look so classical? Tables have definite positions. Planets follow predictable orbits. A cup resting on a desk does not appear to be in a superposition of here and there. Independence seems obvious. Objects seem separate. Measurement outcomes appear stable and objective. The bridge between the quantum formalism and classical appearance began to take shape in the 1970s with the work of Heinz-Dieter Zeh. Zeh introduced what is now called decoherence theory. His insight was that no realistic system is ever perfectly isolated. Every system interacts, even weakly, with its surrounding environment. Those interactions matter. In the abstract mathematics of quantum mechanics, a system can exist in a superposition of states. For example, a particle may be described as being in a superposition of two spatial locations. If the system were perfectly isolated, that superposition would evolve according to the Schrodinger equation without collapsing into a definite outcome. But in practice, isolation is extraordinarily difficult. A dust particle floating in air interacts with billions of air molecules every second. Photons from ambient light scatter off it. Thermal radiation exchanges energy with it. Each interaction entangles the particle with its environment. Zeh recognized that when a system becomes entangled with many environmental degrees of freedom, interference between different components of the system's superposition becomes effectively inaccessible. The coherence between branches of the superposition is dispersed into correlations with the environment. The system does not cease to be described by a quantum state. Instead, its reduced description, obtained by tracing out the environment, becomes approximately diagonal in a certain basis. In plain terms, interference terms between macroscopically distinct states become negligibly small. This process is decoherence. Wojciech Zurek expanded and refined this idea through what he called environment-induced decoherence. Zurek emphasized that the environment does not simply destroy quantum coherence randomly. It selects certain preferred states, known as pointer states, that remain stable under environmental monitoring. Pointer states are those system states that become least entangled with the environment or whose correlations with the environment are robust. For a macroscopic object like a dust grain, pointer states correspond closely to well-defined positions in space. This is why objects appear localized rather than smeared across possibilities. The timescale for decoherence can be astonishingly short. For a dust particle roughly 1 micrometer in diameter, suspended in air at room temperature, decoherence between spatially separated positions differing by even a tiny fraction of a micrometer can occur in times on the order of 10 to the minus 20 seconds. That is a decimal point followed by 19 zeros and then a 1. In everyday terms, effectively instantaneous. The Schrodinger equation still governs the combined system of object plus environment. Nothing in decoherence theory introduces faster than light collapse or modifies the formalism. Instead, the key lies in entanglement. The system becomes correlated with vast numbers of environmental degrees of freedom. Observers, who are themselves physical systems, access only a tiny fraction of the total entangled state. As a result, the reduced state of the system appears classical. Zurek went further and proposed a framework known as quantum Darwinism. The name is evocative but precise in intent. The central idea is that certain states of a system proliferate their information redundantly into the environment. Many independent fragments of the environment carry information about the same preferred states. Imagine a tree in a forest. Light scatters off its surface in all directions. Photons carry information about the tree's position and shape to countless observers. Each observer intercepts only a small subset of those photons, yet they all agree on the tree's location. In quantum Darwinism, the environment acts as a communication channel that broadcasts information about pointer states. These states become effectively objective because multiple observers can independently access consistent information without disturbing the system significantly. This redundancy is crucial. If information about a system were stored in only one fragile environmental degree of freedom, objectivity would not emerge. But when information is copied many times across the environment, stability and consensus arise. In this picture, classical reality is not fundamental. It emerges from quantum entanglement between systems and their environments. The appearance of independence also becomes clearer. When two macroscopic objects are well separated, their environments effectively monitor them independently. Decoherence suppresses interference between macroscopically distinct states so rapidly that superpositions do not survive long enough to produce observable effects. From the perspective of the reduced description available to observers, each object appears to possess its own definite properties. The underlying joint state of the universe may still be highly entangled, but the local reduced states behave approximately classically. This shift reframes the earlier tension about separability. Classical independence is not built into the fundamental equations. It arises under conditions where decoherence has rendered interference between different branches negligible. It is worth emphasizing that decoherence does not by itself solve every interpretational question. It explains why certain outcomes appear stable and why interference is not observed at macroscopic scales. It does not specify which outcome is realized in a single measurement event under every interpretation. Different interpretations, such as many worlds or objective collapse theories, incorporate decoherence in different ways, yet the empirical content of decoherence theory is strong. Experiments in quantum optics and mesoscopic physics have directly observed decoherence effects. Interference patterns disappear when systems are allowed to interact with uncontrolled environments and reappear when isolation is improved. For example, superconducting qubits used in quantum computing experiments must be shielded carefully from environmental noise. Decoherence times in such systems may range from microseconds to milliseconds depending on design. Engineers invest enormous effort into extending these times precisely because environmental entanglement rapidly degrades coherent quantum behavior. These laboratory results mirror the theoretical predictions of Zay and Zurek. Entanglement with the environment spreads phase information into degrees of freedom that are effectively inaccessible. Interference becomes practically impossible to observe. The key insight is that entanglement is not rare. It is ubiquitous. Everything interacts. Everything becomes correlated with its surroundings. What changes between microscopic and macroscopic scales is not the presence of entanglement, but its consequences. At small scales, systems can be sufficiently isolated to maintain coherent superpositions. At large scales, environmental entanglement proliferates so rapidly that classical behavior dominates. Thus, classical reality, with its definite positions and separable objects, emerges as an approximation valid in regimes where decoherence suppresses quantum interference. Independence is not a fundamental principle inscribed at the base of physics. It is a stable pattern that arises from the interplay between quantum systems and their environments. The world appears classical not because quantum mechanics fails, but because quantum entanglement with the environment is overwhelmingly effective. In this light, the earlier puzzles take on a new tone. Entanglement does not sit at the edge of physics as an exotic exception. It is the very mechanism through which the classical world we experience becomes stable and predictable. The independence of everyday objects is real in practice. It is just not fundamental in principle. Once entanglement is accepted as experimentally real and structurally central to quantum theory, a deeper question naturally follows. What does it mean? The equations are clear. The predictions are precise. Bell inequalities are violated. Decoherence explains the emergence of classical appearance. Yet the ontology, the account of what truly exists, remains open to interpretation. Several major interpretations of quantum mechanics offer different answers, especially when it comes to entanglement. The Copenhagen interpretation, historically associated with Niels Bohr and Werner Heisenberg, is perhaps the most well-known. In this view, the quantum state does not describe an objective physical reality in the same way classical states do. Instead, it encodes information about possible measurement outcomes. Bohr emphasized complementarity. Certain experimental arrangements reveal wave-like behavior, others reveal particle-like behavior, but no single description captures both simultaneously. The meaning of physical quantities depends on the measurement context. Observables do not possess definite values independent of the experimental setup. In the Copenhagen perspective, entanglement reflects the fact that quantum systems cannot always be assigned independent states prior to measurement. When two particles are entangled, the joint state describes potential correlations. Upon measurement, one outcome becomes actual, and the formalism updates accordingly. The so-called collapse of the wave function is often described in this interpretation as a change in knowledge or description, rather than a physical signal traveling between particles. The formalism is a tool for predicting probabilities of outcomes observed in classical measurement apparatus. Copenhagen is operationally modest. It does not attempt to describe an underlying microscopic reality beyond what can be measured. It accepts the formalism as complete and refrains from speculating about hidden mechanisms. For some, this restraint is appealing. For others, it feels unsatisfying. Hugh Everett offered a dramatically different proposal in 1957. His many worlds interpretation removes collapse entirely. According to Everett, the Schrodinger equation governs all physical processes, including measurement, without exception. When a measurement occurs on an entangled system, the combined state of system plus apparatus evolves into a superposition of branches, each corresponding to a different outcome. In one branch, the apparatus records spin up. In another, it records spin down. Both branches persist within the universal wave function. Entanglement in this view is not a temporary puzzle, but the engine of branching. Measurement entangles the system with the measuring device, and ultimately with observers. Each possible outcome corresponds to a distinct branch of the global state. There is no collapse. There is no need for hidden variables. The price is ontological abundance. Reality becomes a vast branching structure of decohering worlds. David Wallace and other modern proponents have developed decision-theoretic arguments, attempting to derive the Born rule within this framework. Decoherence plays a central role by explaining why branches effectively cease to interfere with one another. Many worlds retains locality at the level of the Schrodinger equation, but redefines what is meant by a single outcome. Entanglement is universal and never undone. Independence between branches emerges only through decoherence. A third approach, originally proposed by David Bohm in 1952, takes yet another path. Bohmian mechanics, sometimes called pilot wave theory, introduces definite particle positions guided by a wave function. In this framework, particles always possess precise positions. The wave function evolves according to the Schrodinger equation and influences particle motion through what Bohm called the quantum potential. The guidance equation can be written in words as the velocity of a particle equals Planck's constant, divided by mass multiplied by the imaginary part of the gradient of the wave function, divided by the wave function. This guidance relation ensures that particle trajectories reproduce quantum predictions when initial positions are distributed according to the Born rule. Entanglement in Bohmian mechanics manifests as non-local guidance. The wave function of a composite system lives in configuration space, not ordinary three-dimensional space. As a result, the motion of one particle can depend instantaneously on the configuration of another distant particle through the shared wave function. Basil Hiley and others have further developed this framework, exploring its implications for quantum field theory and information. Bohmian mechanics preserves realism in the sense that particles have definite positions, but it sacrifices locality at the fundamental level. It is explicitly non-local, though still constructed to avoid faster-than-light signaling at the level of observable phenomena. Another interpretation, more recent and philosophically distinct, is cubism, short for quantum Bayesianism. Christopher Fuchs and collaborators have advanced this view. Cubism treats the quantum state not as a description of objective reality, but as a representation of an individual agent's degrees of belief about future experiences. In cubism, probabilities are personal and Bayesian. The Born rule is interpreted as a normative rule guiding how agents should update their expectations in light of possible actions and experiences. Entanglement does not represent a mysterious physical bond across space. It encodes an agent's expectations about correlations between experiences resulting from measurements. Cubism does not deny the existence of an external world. Rather, it reframes quantum theory as a tool for agents interacting with that world. The wave function does not exist independently in space. It exists in the agent's bookkeeping of probabilities. This approach avoids ontological extravagance and non-local hidden variables, but it shifts the focus toward experience and information. Across these interpretations, the empirical predictions remain identical. All reproduce the Born rule. All agree on the violation of Bell inequalities. All predict decoherence and its consequences. No currently known experiment distinguishes decisively among them. The differences lie in ontology and explanatory style. Copenhagen emphasizes measurement and classical description. Many worlds embraces universal entanglement and branching structure. Bohmian mechanics restores definite trajectories at the cost of explicit non-locality. Cubism recasts the wave function as an agent-centered tool for managing expectations. Each interpretation must account for entanglement. None can deny it. They disagree on what it represents. Does entanglement reflect a branching multiverse, a non-local guiding field, an update in knowledge, or a structure in an agent's probabilistic expectations? The mathematics remains unchanged. The physical predictions remain the same. This situation is unusual in science. In most areas, competing theories make different empirical claims. Here, interpretation operates at a different level. It concerns what the formalism means rather than what it predicts. For many working physicists, this plurality is tolerable. The equations work. The experiments agree. Technologies such as quantum cryptography and quantum computing proceed without needing to settle the ontology. Yet the interpretational debate continues because entanglement challenges deep intuitions about independence, locality, and reality. Perhaps the most important point is this. Regardless of interpretation, entanglement is not an optional extra. It is embedded in the mathematical structure of quantum theory. Any interpretation must explain why composite systems are described by non-factorizable states, and why Bell inequalities are violated. The interpretations differ in how they describe what exists beneath or alongside that structure. They do not differ in how nature behaves in the laboratory. In that sense, entanglement is experimentally settled but conceptually open. It anchors the theory empirically while leaving space for philosophical exploration. And in that quiet space between equation and meaning, the deeper implications of quantum structure continue to unfold. So far, entanglement has often been described in terms of particles, two photons emitted from the same source, two spins prepared in a singlet state, pairs of systems that interact and then separate. But modern physics does not treat particles as the most fundamental entities. The deeper framework is quantum field theory. In this description, the basic ingredients of nature are fields that extend throughout space and time. Electrons are excitations of the electron field. Photons are excitations of the electromagnetic field. Quarks arise from quark fields. Even what appears as empty space is filled with quantum fields. Within this framework, entanglement is not something added later when two particles collide. It is woven into the structure of the fields themselves. One mathematically rigorous approach to quantum field theory is known as algebraic quantum field theory. Rudolf Hegg played a central role in developing this formulation in the 1950s and 1960s. Instead of focusing primarily on particle states, algebraic quantum field theory emphasizes local algebras of observables assigned to regions of spacetime. In this approach, each spacetime region is associated with a set of operators representing measurable quantities within that region. These local algebras satisfy precise mathematical properties, including locality conditions. Observables associated with space-like separated regions commute, ensuring compatibility with special relativity. What is striking is that even in the vacuum state, the lowest energy state of the field with no particles present, there is entanglement between different regions of space. This idea can feel counterintuitive. Vacuum suggests emptiness. Yet in quantum field theory, the vacuum is not a simple void. It is a highly structured state, with fluctuations arising from the uncertainty principle. If one divides space into two regions separated by a boundary, the vacuum state of the quantum field does not factorize into a simple product of a vacuum for region A and a vacuum for region B. Instead, the global vacuum is entangled across the boundary. This is not a speculative claim. It follows from the mathematical structure of quantum fields and has been explored rigorously in algebraic quantum field theory. A particularly deep result in this context is the Rie-Schlieder theorem. Named after Helmut Rie and Siegfried Schlieder, this theorem states, roughly speaking, that by applying local operators within any non-trivial region of spacetime to the vacuum state, one can approximate any state in the Hilbert space arbitrarily well. Conceptually, this means that the vacuum is highly entangled across space-like regions. Local operations in one region have access in principle to the full richness of the global state. This does not imply faster-than-light signaling. The commutation of observables in space-like separated regions still guarantees that local measurements cannot transmit information superluminally. Instead, the theorem highlights the depth of entanglement embedded in the vacuum itself. The vacuum is not a simple, separable background. It is a globally correlated state. Another remarkable consequence of quantum field theory in curved or accelerated frames is the Unruh effect, predicted by William Unruh in 1976. According to the Unruh effect, an observer undergoing constant acceleration will perceive the vacuum as a thermal bath of particles. In other words, what an inertial observer describes as empty space appears warm to an accelerating observer. The temperature associated with this effect is proportional to the acceleration. In everyday units, the acceleration required to produce even a tiny temperature is enormous, far beyond ordinary experience. Nevertheless, the theoretical prediction arises directly from the structure of quantum fields and their entanglement across spacetime regions. The Unruh effect reflects how the vacuum state is entangled between different modes defined relative to different observers. When one restricts attention to a subset of spacetime accessible to an accelerating observer, the reduced state appears thermal. The apparent temperature arises from tracing out inaccessible degrees of freedom beyond the observer's horizon. This phenomenon parallels ideas in black hole physics. Stephen Hawking showed in 1974 that black holes radiate thermally due to quantum effects near the event horizon. The Hawking radiation process can also be understood in terms of entanglement between modes inside and outside the horizon. These examples demonstrate that entanglement in quantum field theory is not limited to carefully prepared laboratory systems. It is a pervasive feature of the vacuum and of spacetime itself. In ordinary particle physics experiments such as those conducted at the Large Hadron Collider at CERN, entanglement appears routinely in scattering processes and decay products. When particles are created in high-energy collisions, conservation laws often enforce correlated properties, such as total spin or momentum. The resulting states are entangled by construction. Yet even before any collision occurs, the fields filling space are already entangled across regions. This shifts the perspective once again. Entanglement is not an anomaly produced by special preparation. It is the natural state of quantum fields. In algebraic quantum field theory, the assignment of local algebras to regions highlights a tension between locality of observables and global entanglement of states. Observables in space-like separated regions commute, preserving relativistic causality. At the same time, the global state, including the vacuum, may be highly entangled. The structure is subtle but consistent. Local measurements cannot influence distant outcomes in a way that violates special relativity. Yet the statistical correlations between regions reflect a shared global structure. The independence of distant regions, assumed in classical field theory, no longer holds at the level of quantum states. Instead, the vacuum itself encodes correlations across space. One way to visualize this is to imagine dividing space into two halves. Even if no particles are present, the quantum field in one half cannot be described independently of the field in the other half. The global vacuum state contains correlations that link them. This entanglement has measurable consequences. In condensed matter physics, similar ideas lead to the concept of entanglement entropy, which quantifies how much entanglement exists between regions. In quantum field theory, entanglement entropy typically scales with the area of the boundary, separating regions rather than their volume. This area law behavior has deep connections to gravitational physics and the holographic principle. The central message is steady and clear. Entanglement is not an optional add-on to quantum theory. It is embedded in the fabric of quantum fields. It persists even in what appears to be empty space. It respects relativistic causality while reshaping the notion of separability. Particles may come and go. Fields fluctuate. Observers move inertially or accelerate. Throughout it all, the underlying structure remains entangled, and once entanglement is recognized as intrinsic to the vacuum and to spacetime regions themselves, the question of connection becomes even more profound. The links between distant regions are not imposed from outside. They arise from the fundamental architecture of quantum field theory. What once seemed like a peculiar feature of specially prepared particle pairs becomes, at this level, a pervasive aspect of the quantum world itself. Entropy began as a measure of heat and disorder. In the 19th century, Ludwig Boltzmann connected thermodynamics to microscopic physics by proposing that entropy reflects the number of microscopic configurations consistent with a macroscopic state. His famous formula, engraved on his tombstone in Vienna, can be written in words as entropy equals Boltzmann's constant, multiplied by the natural logarithm of the number of microstates. That equation expresses a powerful idea. When many microscopic arrangements correspond to the same large-scale description, entropy is high. When only a few arrangements are compatible, entropy is low. In classical statistical mechanics, entropy quantifies ignorance about the exact microscopic state. A gas in a box contains an enormous number of molecules, each with its own position and velocity. It would be impractical to specify all of them individually. Instead, one describes macroscopic quantities such as temperature and pressure. The entropy reflects the number of microscopic arrangements that give rise to those macroscopic values. Quantum mechanics reframes this picture. John von Neumann generalized the concept of entropy to quantum systems. Instead of counting classical microstates, he defined entropy in terms of the density matrix, a mathematical object that encodes probabilities for quantum states. The von Neumann entropy is written in words as entropy equals minus the trace of the density matrix multiplied by the natural logarithm of the density matrix. Although that expression may sound abstract, its meaning parallels Boltzmann's idea. If a quantum system is in a pure state, meaning it is described by a single state vector with complete coherence, its von Neumann entropy is zero. There is no uncertainty about the state. If the system is in a mixed state, representing a statistical mixture of possibilities, the entropy is greater than zero. The density matrix formalism is especially useful when dealing with subsystems of a larger entangled whole. Suppose two systems are entangled and described by a joint pure state. The composite system may have zero von Neumann entropy. However, if one focuses only on one subsystem and traces out the other, the reduced density matrix typically describes a mixed state. This reduced state carries non-zero entropy. The entropy is called entanglement entropy when it arises purely from tracing out part of an entangled system. It measures how strongly the subsystem is correlated with the rest of the system. To understand this intuitively, imagine two qubits prepared in a maximally entangled state. The joint system is in a pure state. Yet if one examines only one qubit, its reduced density matrix assigns equal probability to two outcomes. The single qubit appears completely random. Its entropy is maximal. The randomness does not reflect ignorance about a hidden variable. It reflects entanglement with the other qubit. Entanglement entropy therefore quantifies how information is distributed across subsystems. This concept connects directly to Boltzmann's statistical mechanics. In classical thermodynamics, entropy often increases because microscopic correlations become inaccessible. In quantum mechanics, entanglement spreads correlations across degrees of freedom. When a subsystem is considered in isolation, its entropy increases as it becomes entangled with its environment. Decoherence, discussed earlier, can be described in these terms. As a system interacts with its environment, entanglement entropy between them grows. The reduced state of the system becomes mixed. Interference terms fade. Classical probabilities emerge. This is not entropy in the sense of disorder alone. It is entropy as a measure of quantum correlation. The idea that entanglement distributes information rather than destroying it is central. When two systems become entangled, information about one system is encoded in correlations with the other. The joint state retains coherence, but the local description appears uncertain. In many body physics, entanglement entropy has become a powerful diagnostic tool. Researchers studying quantum phase transitions examine how entanglement entropy scales with system size. In one-dimensional systems with short-range interactions, ground states often obey an area law. The entanglement entropy between a region and its complement scales with the boundary between them rather than the volume of the region. This is surprising from a classical perspective. Classical correlations typically scale with volume. Quantum entanglement, however, often scales with area. This area scaling appears not only in condensed matter systems, but also in quantum field theory, as mentioned earlier. When space is divided into two regions, the entanglement entropy of the vacuum typically scales with the area of the boundary separating them. Such scaling hints at a deep connection between entanglement and geometry. Before reaching geometry, it is helpful to emphasize the informational perspective. In classical information theory, developed by Claude Shannon in 1948, entropy measures the average uncertainty of a random variable. Shannon entropy is defined in words as entropy equals minus the sum over probabilities of probability multiplied by the natural logarithm of probability. Von Neumann entropy generalizes this to quantum systems. When the density matrix is diagonal in some basis, the von Neumann entropy reduces to Shannon entropy for the corresponding probability distribution. Entanglement entropy, therefore, can be interpreted as a measure of how much information about one subsystem is encoded non-locally in correlations with another. This viewpoint aligns with developments in quantum information science. Entanglement is treated as a resource. It enables quantum teleportation, superdense coding, and certain computational speedups. These protocols rely on the distribution of information across subsystems in ways impossible for classical systems. Consider quantum teleportation, first proposed by Charles Bennett and colleagues in 1993. Teleportation does not transmit matter or energy instantaneously. Instead, it transfers quantum information using shared entanglement and classical communication. The success of the protocol depends on the entanglement entropy between the participating systems. Entanglement entropy thus becomes a quantitative bridge between foundational physics and practical information processing. It also prepares the ground for deeper theoretical developments. In black hole physics, Jacob Bekenstein and Stephen Hawking discovered that black hole entropy is proportional to the area of the event horizon. This area law echoes the behavior of entanglement entropy in quantum field theory. Such parallels suggest that entropy and geometry may be intertwined more profoundly than classical thermodynamics anticipated. At this stage, a pattern emerges. Entanglement reshapes locality. It challenges separability. It underlies decoherence and classical appearance. It defines new forms of entropy. And it distributes information across subsystems in ways that classical correlations cannot replicate. The classical picture of independent parts, each carrying their own information, gives way to a network of correlations woven through quantum states. Entropy, once a measure of disorder in steam engines and gas cylinders, now measures the depth of quantum connection between regions of space and between subsystems of a field. And as entanglement entropy reveals its area-scaling behavior and its link to horizons and boundaries, a new possibility begins to take shape. Perhaps geometry itself, the structure of spacetime, is related to patterns of entanglement. That possibility lies just beyond the horizon of information theory, where quantum structure meets gravitational physics. In classical physics, geometry comes first. Space is a stage. Distances are measured by rulers. Angles are defined by straight lines. Matter moves within a pre-existing arena. Even in general relativity, where spacetime is dynamical and curved by mass and energy, geometry remains fundamental. The Einstein field equations state, in words, spacetime curvature equals 8π multiplied by the gravitational constant divided by the speed of light to the fourth power, multiplied by the stress energy tensor. Geometry responds to matter, but geometry itself is still a primary ingredient. In recent decades, a different possibility has gained attention. What if space-time geometry is not fundamental? What if it emerges from patterns of quantum entanglement? This idea began to crystallize in the 1990s with the holographic principle, proposed independently by Gerard 't Hooft and later refined by Leonard Susskind. The inspiration came from black hole thermodynamics. Jacob Bekenstein and Stephen Hawking discovered that the entropy of a black hole is proportional not to its volume, but to the area of its event horizon. Specifically, the entropy is proportional to the area divided by 4 times Planck length squared. The Planck length is an extraordinarily small scale, roughly 1.6 times 10 to the minus 35 meters. The appearance of area rather than volume suggested something profound. In ordinary systems, entropy scales with volume. More space usually means more degrees of freedom. Black holes defy this expectation. Their entropy scales with surface area. The holographic principle takes this observation seriously. It proposes that the information content of a region of space can be encoded on its boundary, much like a hologram encodes three-dimensional information on a two-dimensional surface. If correct, this principle implies that the fundamental description of a volume of space might reside on its lower dimensional boundary. A dramatic realization of this idea came in 1997, when Juan Maldacena proposed the anti-de Sitter/conformal field theory correspondence, often called ADS/CFT. Maldacena suggested that a quantum theory of gravity defined in a higher dimensional spacetime with anti-de Sitter geometry is mathematically equivalent to a conformal field theory defined on its lower dimensional boundary. In simpler terms, physics in a curved spacetime with gravity can be equivalent to a quantum field theory without gravity living on the boundary of that spacetime. This correspondence is not a loose analogy. It is a precise mathematical duality supported by extensive calculations. In this framework, the extraspatial dimension of the gravitational theory emerges from properties of the boundary field theory. Entanglement plays a central role in this emergence. In 2006, Shinsei Ryu and Tadashi Takayanagi proposed a remarkable formula connecting entanglement entropy in the boundary theory to geometry in the bulk gravitational spacetime. The Ryu-Takayanagi formula states, in words, the entanglement entropy of a region in the boundary theory equals the area of a minimal surface in the bulk spacetime divided by 4 times the gravitational constant. This formula echoes the black hole entropy relation. It ties a purely quantum information quantity, entanglement entropy, to a geometric area in a higher dimensional space. In the AD-CFT context, if one takes a region of the boundary conformal field theory and computes its entanglement entropy, that entropy corresponds to the area of a surface extending into the bulk anti-de Sitter space that is anchored on the boundary of the chosen region. Geometry appears to encode entanglement. The implication is extraordinary. The connectivity and curvature of spacetime in the bulk may reflect how strongly different regions of the boundary theory are entangled. If entanglement between boundary regions changes, the geometry of the bulk adjusts accordingly. In some scenarios, reducing entanglement between 2 regions of the boundary can cause the bulk spacetime connecting them to pinch off or disconnect. This line of thought suggests that spacetime itself might be woven from entanglement. Parallel insights have emerged from tensor network models developed in quantum many-body physics. Guillaume Vidal introduced the multiscale entanglement renormalization ansatz, commonly abbreviated as MIRA. MIRA is a tensor network designed to efficiently represent quantum states with specific entanglement structures, especially in systems near critical points. In a tensor network, the quantum state of a many-body system is represented as a network of interconnected tensors. The pattern of connections reflects how entanglement is distributed across scales. Remarkably, the geometry of certain tensor networks resembles the geometry of anti-de Sitter space. The hierarchical structure of MIRA, with layers corresponding to different length scales, mirrors the radial direction in ADS spacetime. Each layer in the network can be interpreted as encoding degrees of freedom at a different scale, similar to how the extra dimension in AD-CFT corresponds to energy scale in the boundary theory. This resemblance is not merely aesthetic, it reinforces the idea that geometric structure may arise from entanglement patterns. If quantum states can be represented as networks whose connectivity defines an emergent geometry, then geometry itself may not be fundamental. It may be a large-scale manifestation of quantum correlations. This perspective reframes earlier discussions about separability. Classical geometry assumes that points in space are distinct and separated by well-defined distances. If geometry emerges from entanglement, then distance itself may reflect how strongly subsystems are correlated. Two regions that are highly entangled might be considered close in the emergent geometry. Regions with little entanglement might be far apart. Leonard Susskind has described entanglement as the glue holding spacetime together. This metaphor captures the intuition without overstating certainty. The precise mechanisms remain under investigation, but the mathematical connections are compelling. It's important to emphasize that these ideas are most rigorously developed in specific theoretical settings, particularly anti-de Sitter space. Our observable universe appears to have a positive cosmological constant rather than the negative curvature of anti-de Sitter geometry. Extending holographic ideas to realistic cosmology remains an active area of research. Nevertheless, the conceptual shift is clear. Entanglement is no longer viewed solely as a feature of particle pairs or laboratory systems. It may underpin the structure of spacetime itself. The holographic principle suggests that information scales with area. The AD-CFT correspondence provides a concrete duality linking gravitational geometry and quantum field theory. The Ryu-Takayanagi formula ties entanglement entropy directly to geometric surfaces. Tensor network models offer intuitive pictures of how entanglement patterns can generate spatial structure. Across these developments, a common theme appears. Geometry and entanglement are intertwined. The classical image of space-time as a fixed backdrop gives way to a more relational view. Spacetime may emerge from the quantum state of underlying degrees of freedom. Distances and curvature could reflect patterns of correlation. If that is the case, then the earlier question about how distant things remain connected acquires a deeper layer. Perhaps distance itself is not fundamental. Perhaps what appears as spatial separation arises from the structure of entanglement in a more basic quantum description. These ideas remain at the frontier of theoretical physics. They are mathematically sophisticated and not yet confirmed by direct experiment in the context of quantum gravity. Yet they represent a serious and ongoing attempt to unify quantum theory with gravitational geometry. In this view, entanglement is not merely a curious quantum feature. It may be the scaffolding from which spacetime is built. And if spacetime geometry reflects entanglement structure, then the connection between distant regions is not an anomaly within space. It may be a hint about how space itself comes into being. In 1935, two seemingly separate ideas entered physics almost simultaneously. One was the Einstein-Podolsky-Rosen paper, questioning the completeness of quantum mechanics and highlighting entanglement. The other was a solution to Einstein's equations discovered by Albert Einstein and Nathan Rosen, describing what is now called an Einstein-Rosen bridge. At the time, these ideas were unrelated. One concerned quantum correlations. The other concerned spacetime geometry and general relativity. Decades later, in 2013, Juan Maldacena and Leonard Susskind proposed a bold conjecture linking them. They suggested that ER equals EPR. In words, Einstein-Rosen bridges are equivalent to Einstein-Podolsky-Rosen entanglement. To unpack this, it helps to recall what an Einstein-Rosen bridge is. In general relativity, certain solutions to the Einstein field equations describe black holes. When extended mathematically, some of these solutions contain a structure connecting two asymptotically separate regions of spacetime. This structure resembles a tunnel or throat linking distant regions. It is often called a wormhole. The simplest such object is a non-traversable wormhole. It connects two regions geometrically, but no signal or object can pass through it from one side to the other. The throat pinches off too quickly, and any attempt to cross would encounter extreme gravitational effects. The key point is that an Einstein-Rosen bridge represents a topological connection in spacetime. Two regions that appear distant in ordinary space may be connected through a higher dimensional geometry. Maldacena and Suskind's conjecture proposes that certain entangled quantum states are equivalent, in a precise theoretical sense, to spacetime geometries containing such bridges. In particular, they considered pairs of black holes prepared in a maximally entangled state. Within the anti-de Sitter/conformal field theory framework, such a pair can be described as two black holes connected by a non-traversable wormhole. The entanglement between the two systems corresponds to the geometric connection in the bulk spacetime. This idea does not suggest that entangled particles in a laboratory are literally connected by tiny traversable tunnels. Instead, it proposes a deep equivalence between quantum entanglement and geometric connectivity at a fundamental level. The slogan ER equals EPR captures this equivalence succinctly. ER stands for Einstein-Rosen bridge. EPR stands for Einstein-Podolsky-Rosen entanglement. The conjecture remains theoretical. It is grounded in the mathematical structure of holographic dualities, particularly within anti-de Sitter spacetime. It does not yet have direct empirical confirmation in our observable universe. Nonetheless, it builds on solid theoretical foundations. The anti-de Sitter/conformal field theory correspondence, proposed by Maldacena in 1997, provides a concrete setting in which gravitational geometry and quantum entanglement are mathematically linked. The Ryu-Takayanagi formula already connects entanglement entropy to minimal surface areas in the bulk. ER equals EPR extends this connection. It suggests that entanglement may be understood as a form of spacetime connectivity. It is essential to clarify what this does and does not mean. It does not mean that entanglement allows faster-than-light travel through wormholes. The Einstein-Rosen bridges considered in these models are non-traversable. No signal can pass through them. Causality remains intact. It does not mean that laboratory-scale entanglement experiments have revealed microscopic wormholes directly. The conjecture operates at a level of theoretical description within specific models of quantum gravity. What it does mean is that entanglement might have a geometric interpretation. Instead of thinking of entangled systems as mysteriously correlated across empty space, one might think of them as connected through a deeper topological structure in an underlying spacetime. In this view, distance and connectivity are not purely geometric primitives. They may arise from entanglement patterns. Topology, the mathematical study of connectedness and continuity, becomes central. Two regions of space that are far apart in ordinary coordinates might nonetheless be connected in a higher dimensional description. Conversely, reducing entanglement between regions might correspond to tearing or separating spacetime in the bulk geometry. These ideas are speculative but not arbitrary. They are motivated by consistent mathematical frameworks in string theory and holography. Researchers continue to explore how robust the ER equals EPR conjecture is beyond idealized anti-de Sitter settings. There are also intriguing links to quantum information. In some thought experiments, such as those involving black hole evaporation and the information paradox, entanglement structure plays a crucial role in maintaining consistency with unitarity and avoiding contradictions. The Hayden-Preskill thought experiment, for example, analyses how quickly information thrown into a black hole can be recovered from Hawking radiation under certain entanglement assumptions. These considerations reinforce the centrality of entanglement in gravitational contexts, yet caution is warranted. The ER equals EPR conjecture is not experimentally verified in the way Bell inequality violations are. It is part of an ongoing theoretical effort to unify quantum mechanics and general relativity. Its strength lies in the coherence of the mathematical structures involved. Holographic dualities, minimal surfaces, and entanglement entropy calculations all point toward a deep relationship between geometry and quantum correlations. What once appeared as a puzzling non-local correlation might be reinterpreted as a reflection of hidden connectivity in spacetime. If entanglement corresponds to geometric bridges, then the phrase distant things may require refinement. They may be distant according to one coordinate system, yet connected in another, more fundamental description. This does not eliminate the need for careful reasoning about causality and signaling. Non-traversable wormholes do not permit shortcuts for information transfer. The no-signaling theorem remains in force. Instead, the emphasis shifts from signaling to topology. Entanglement becomes less about instantaneous influence and more about shared structure. The universe, in this speculative but mathematically grounded picture, is not composed of isolated islands separated by empty void. It is a network of correlations whose geometry reflects those correlations. Whether this vision fully captures the nature of spacetime remains an open question. What is clear is that entanglement has moved from the margins of quantum theory to the heart of attempts to understand gravity and geometry. And in that movement, the idea of connection acquires a new meaning, not as a signal racing through space, but as a fundamental link in the architecture of reality itself. For much of the 20th century, quantum mechanics was viewed primarily as a theory about atoms, particles, and fields. Its strange features were interpreted as constraints on microscopic behavior. Toward the end of that century, a shift occurred. Researchers began to treat quantum theory not only as a description of nature, but as a framework for processing information. Quantum information theory emerged from this shift. In 1984, Charles Bennett and Gilles Brassard introduced a protocol for secure communication known as BB84. Their idea was simple and profound. By encoding information in quantum states and exploiting the fact that measurement disturbs those states, two parties could detect the presence of an eavesdropper. Security would rest not on computational difficulty, but on the laws of physics. This marked a turning point. Quantum features such as superposition and entanglement were no longer viewed solely as conceptual puzzles. They became resources. The basic unit of quantum information is the qubit, short for quantum bit. A classical bit takes one of two definite values, 0 or 1. A qubit can exist in a superposition of both possibilities simultaneously. Mathematically, it is described by a state vector in a two-dimensional Hilbert space. In words, one may say that a qubit state is a linear combination of 0 and 1 with complex amplitudes. When measured in a particular basis, the probabilities of obtaining 0 or 1 are determined by the squares of those amplitudes, according to the Born rule. The power of qubits becomes more apparent when they are combined. Two classical bits can represent four distinct combinations, 0, 0, 0, 1, 1, 0, or 1, 1. Two qubits, by contrast, can exist in a superposition of all four combinations at once. More importantly, they can be entangled. Entanglement provides correlations that cannot be simulated efficiently by classical systems. It enables protocols such as quantum teleportation and superdense coding. In superdense coding, one can transmit two classical bits of information by sending a single qubit, provided that the communicating parties share an entangled pair beforehand. The resource character of entanglement invites quantification. How much entanglement does a given state contain? Can it be increased, decreased, or transformed? William Wouters addressed part of this question in the late 1990s by introducing a measure known as concurrence for pairs of qubits. Concurrence provides a numerical value between 0 and 1 that quantifies the degree of entanglement in a 2-qubit state. A value of 0 corresponds to a separable state. A value of 1 corresponds to a maximally entangled state. Concurrence is derived from the density matrix of the 2-qubit system through a specific mathematical procedure involving eigenvalues. Although the calculation can be technical, the conceptual purpose is straightforward. It assigns a clear number to how strongly the qubits are entangled. This quantification is essential because entanglement behaves differently from classical correlations. It cannot be increased by local operations and classical communication alone. If two parties share a weakly entangled state, they cannot simply apply local transformations to make it strongly entangled without additional resources. However, they can perform a process known as entanglement distillation. By starting with multiple copies of weakly entangled states and performing coordinated local operations combined with classical communication, they can sometimes extract a smaller number of states with higher entanglement. Entanglement distillation highlights the idea that entanglement is a consumable resource. It can be diluted, concentrated, or expended in communication tasks. This perspective has been formalized in what is known as resource theory. In resource theory, one defines a set of free operations and a set of valuable resources. For entanglement theory, local operations and classical communication are typically considered free operations. Entangled states are valuable resources because they enable tasks that free operations alone cannot accomplish. Researchers including Fernando Brandão have contributed to developing rigorous frameworks for understanding entanglement as a resource. These frameworks explore which transformations between quantum states are possible under specified constraints, and how entanglement measures behave under those transformations. One key principle in resource theory is monotonicity. A valid entanglement measure should not increase under local operations and classical communication. This ensures that entanglement cannot be created for free. In communication scenarios, entanglement enables protocols that would otherwise be impossible. Quantum teleportation, proposed by Charles Bennett and collaborators in 1993, allows the state of a qubit to be transferred from one location to another using a shared entangled pair and two classical bits of communication. The original qubit state is destroyed in the process, preserving the no-cloning theorem, which states that unknown quantum states cannot be copied perfectly. In computation, entanglement is widely believed to be a crucial ingredient in quantum speedup. Algorithms such as Shor's algorithm for integer factorization and Grover's algorithm for database search exploit superposition and interference. While debate continues about whether entanglement is strictly necessary for all quantum advantages, it is clear that highly entangled states often play a central role in powerful quantum computations. Experimental platforms ranging from superconducting qubits to trapped ions aim to create and maintain entangled states across dozens or even hundreds of qubits. These systems must carefully manage decoherence, since unwanted entanglement with the environment degrades useful entanglement within the computational register. Thus, entanglement functions as both a fragile and powerful asset. It enables tasks beyond classical reach, yet it must be protected from environmental interactions that disperse it. Quantum information theory reframes earlier foundational debates. Instead of asking only what entanglement means philosophically, it asks what entanglement can do operationally. This shift does not eliminate interpretational questions. Rather, it grounds them in practical capability. Entanglement is measurable, manipulable, and economically valuable in an informational sense. The transition from philosophical puzzle to engineered resource illustrates a broader theme in physics. Concepts that once appeared abstract and perplexing often become tools when understood precisely. Entanglement, once invoked as evidence of incompleteness or mystery, now underpins secure communication systems and the pursuit of quantum computers. In this context, information is not merely a metaphor. It is a physical quantity constrained by quantum laws. Entanglement determines how information is distributed across subsystems, how it can be concentrated, and how it can be harnessed. And as quantum information theory continues to evolve, it strengthens the view that entanglement is not an exotic anomaly at the margins of physics. It is a central currency in the economy of quantum processes, shaping both communication and computation at the most fundamental level. When entanglement first entered physics, it seemed like a philosophical inconvenience. It challenged locality, unsettled realism, and invited long debates. In the closing decades of the 20th century, it began to do something more practical. It started carrying messages. Quantum key distribution is one of the earliest and clearest examples. In 1991, Arthur Eckert proposed an entanglement-based protocol for secure communication. His scheme, often called the Eckert protocol, uses pairs of entangled particles shared between two distant parties. The idea is elegant. Suppose two partners share many pairs of entangled qubits prepared in a maximally entangled state. Each partner measures their qubit along randomly chosen directions. Because of entanglement, their measurement results will be correlated in ways that violate Bell inequalities. Those correlations serve two purposes at once. First, they generate a shared random key that can later be used for encryption. Second, they provide a built-in security test. If an eavesdropper attempts to intercept or measure the particles in transit, the delicate entanglement will be disturbed. The observed correlations will deviate from the expected Bell violation, alerting the legitimate users. Security is no longer based solely on computational assumptions. It rests on the structure of quantum correlations. This is not a thought experiment. Quantum key distribution systems have been implemented in laboratories and deployed in limited commercial networks. The challenge has always been distance, since photons traveling through optical fibers are absorbed or scattered over tens or hundreds of kilometers. To extend the range, researchers have turned to space. Jianwei Pan and his collaborators in China led the development of the Messius satellite, launched in 2016. Messius distributed entangled photon pairs between ground stations separated by more than 1,000 kilometers. These experiments demonstrated satellite-based entanglement distribution on a global scale. The correlations measured between distant stations were consistent with quantum predictions and suitable for secure key generation. The Earth itself became part of the experimental apparatus. Communication is only one side of the story. Computation presents another. In 1994, Peter Shaw introduced an algorithm that startled the computational world. Shaw's algorithm can factor large integers efficiently on a quantum computer. In classical computing, no efficient algorithm is known for factoring large numbers. The best classical methods require time that grows super-polynomially with input size. Shaw showed that a quantum computer could perform this task in polynomial time. The significance is not merely academic. Many widely used cryptographic systems, including the RSA encryption scheme, rely on the practical difficulty of factoring large integers. A sufficiently powerful quantum computer running Shaw's algorithm could, in principle, break such encryption. Shor's algorithm relies on quantum superposition and interference to perform a quantum Fourier transform efficiently. Entanglement plays a key role in correlating different parts of the computational register during the algorithm's execution. Without entanglement, the computational state would factor into independent pieces, and the full quantum advantage would not materialize. 2 years later, in 1996, Love Grover introduced another quantum algorithm. Grover's algorithm addresses a different problem: searching an unsorted database. Classically, searching through n items requires, on average, about n divided by 2 queries. Grover's algorithm can find a marked item in approximately the square root of n steps. This quadratic speedup is more modest than Shor's exponential improvement, yet it is still significant. For large databases, reducing the required number of steps from millions to thousands can matter. Grover's algorithm uses repeated amplitude amplification, a process that increases the probability amplitude of the desired solution while decreasing others. Entanglement often arises during these operations, binding qubits together in ways that classical bits cannot emulate. The exact role of entanglement in quantum speedup remains an active area of research. Some highly mixed quantum states exhibit limited entanglement, yet still provide certain advantages. In other contexts, strong multipartite entanglement appears essential. What is clear is that classical correlations alone cannot reproduce the full behavior of quantum algorithms. The tensor product structure of multi-qubit Hilbert space grows exponentially with the number of qubits. A system of 50 qubits has a state space dimension of 2 raised to the power 50, a number exceeding 1 quadrillion. Simulating such systems exactly on classical computers becomes rapidly infeasible. Entanglement allows quantum computers to explore this vast state space coherently. Interference patterns between amplitudes guide the computation toward desired outcomes. At the same time, entanglement is delicate. Interactions with the environment introduce decoherence, degrading the correlations necessary for computation. This is why quantum computing platforms, whether based on superconducting circuits, trapped ions, or photonic systems, operate at extreme conditions. Superconducting qubits are often cooled to temperatures near absolute zero, measured in millikelvin. Trapped ions are isolated in vacuum chambers and manipulated with finely tuned laser pulses. Engineers strive to maintain coherence long enough to execute sequences of quantum gates. Error correction schemes have been developed to protect quantum information by encoding it across multiple physical qubits, using entanglement to detect and correct errors without measuring the encoded information directly. Thus, entanglement functions as both enabler and vulnerability. It grants computational and communicational power, yet it demands careful protection. The broader lesson is steady. Entanglement is not merely a curiosity about distant particles. It is a working ingredient in real devices. It underlies protocols that secure communication against eavesdroppers. It drives algorithms that challenge classical computational limits. It shapes the architecture of emerging technologies. And throughout these developments, the same principles remain intact. No faster than light signaling occurs. Relativistic causality holds. Bell inequalities are violated within quantum bounds. The mathematical structure of Hilbert space governs every step. The question of how distant things stay connected now acquires a practical dimension. Those connections are not just philosophical puzzles, they are operational tools. Entanglement, once debated in letters between Einstein and Born, now travels between laboratories and satellites. It links qubits in processors and photons across continents. What began as a conceptual challenge has become a technological resource, steadily reinforcing the conclusion that quantum connections are not anomalies in the margins of physics. They are central features of how information can be stored, transmitted, and processed in our universe. Entanglement is often introduced through photons, qubits, and carefully isolated laboratory systems. It can feel delicate, almost fragile, something that survives only in ultra-cold chambers and vacuum lines. Yet some of the most striking manifestations of entanglement occur not in isolation, but in bulk matter. Entire materials owe their properties to collective quantum states that cannot be reduced to independent particles. Superconductivity is one of the clearest examples. In 1957, John Bardeen, Leon Cooper, and Robert Schrieffer proposed what is now known as the Bardeen-Cooper-Schrieffer theory, often abbreviated as BCS theory. They explained how certain materials, when cooled below a critical temperature, conduct electricity with zero resistance. The key idea involves Cooper pairs. In a conventional metal, electrons repel one another due to their negative charge. However, under suitable conditions at low temperature, electrons near the Fermi surface can form bound pairs through interactions mediated by lattice vibrations, known as phonons. These Cooper pairs are not tightly bound like molecules. They are extended quantum objects that overlap with many others. Crucially, they form a coherent collective state. The wave function describing the superconducting ground state is not a product of independent electron states. It is a highly entangled many-body state. In this state, electrons move in correlated pairs across macroscopic distances. The phase of the collective wave function becomes coherent throughout the material. Because scattering processes that would normally cause resistance would require breaking these pairs, electrical resistance vanishes below the critical temperature. Superconductivity, therefore, is not just about electrons behaving nicely. It is about entanglement shaping a material's macroscopic behavior. Topological phases of matter reveal an even deeper role for entanglement. Xiaogang Wen and others have developed the concept of topological order to describe phases that cannot be characterized by conventional symmetry breaking. In such systems, the defining properties are encoded in global patterns of entanglement rather than local order parameters. The fractional quantum Hall effect, discovered experimentally in the 1980s, provides a vivid example. When electrons are confined to two dimensions and subjected to extremely strong magnetic fields at very low temperatures, they can form states with precisely quantized Hall conductance at fractional values. These fractional quantum Hall states cannot be explained by treating electrons as nearly independent particles. Instead, they arise from strongly correlated many-body wave functions. The entanglement structure of these states gives rise to quasi-particles with fractional electric charge and exotic exchange statistics. The topology of the quantum state determines observable properties such as quantized conductance. The system's behavior depends not on microscopic details alone, but on global entanglement patterns. Entanglement entropy has become a powerful diagnostic tool in identifying such topological phases. In two-dimensional systems, the entanglement entropy between a region and its complement often follows an area law with a small correction term known as topological entanglement entropy. This correction encodes information about the underlying topological order. In these systems, entanglement is not an incidental correlation. It is the organizing principle of the phase. Even in more everyday materials, entanglement plays a quiet but pervasive role. Magnetism, for example, arises from quantum mechanical exchange interactions between electron spins. The Heisenberg model describes spin systems whose ground states can exhibit long-range entanglement. In certain regimes, quantum spin liquids emerge, where spins remain highly entangled without forming conventional magnetic order. Such phases defy classical expectations. They cannot be described by assigning definite spin directions to individual sites. Instead, the ground state is a superposition of many configurations, with entanglement linking distant regions. One might imagine that all of this remains confined to microscopic scales, yet experiments in optomechanics have begun to push entanglement toward larger systems. In optomechanical setups, tiny mechanical resonators, sometimes micrometer-scale mirrors or membranes, are coupled to electromagnetic fields inside cavities. By carefully controlling laser light and cooling techniques, researchers have generated entanglement between mechanical oscillators and optical modes. In some experiments, mechanical resonators containing billions of atoms have been placed into states exhibiting quantum coherence and entanglement. While these systems are still far from everyday objects like chairs or cats, they bridge the gap between microscopic and mesoscopic scales. Maintaining such states requires extreme isolation and precise control. Even slight thermal interactions can destroy coherence. Yet the fact that entanglement can be engineered in systems containing large numbers of particles demonstrates that quantum correlations are not confined to the smaller scales by principle. They are limited in practice by decoherence. These developments reinforce a broader theme. Entanglement is not merely a feature of isolated pairs, it is foundational to the properties of materials. The electrical resistance of a wire at low temperature, the quantist conductance of a two-dimensional electron gas, the emergence of exotic quasi-particles, and the coherent oscillations of mechanical resonators all trace back to collective quantum states. In classical thinking, material properties arise from local interactions between independent constituents. In quantum condensed matter physics, the collective wave function of many particles, often deeply entangled, determines the phase and behavior of the material. This shift in perspective mirrors earlier themes. Independence is not fundamental. Correlations shape reality. Materials that appear stable and classical at large scales are underpinned by quantum mechanical interactions at the microscopic level. In some phases, entanglement is subtle and largely hidden. In others, it becomes the defining feature. Superconductors carry currents without resistance because electrons pair in an entangled state. Topological materials exhibit robust properties because of global entanglement patterns. Quantum Hall systems display precise conductance plateaus due to collective correlations. The connection between distant parts of a material is not metaphorical, it is encoded in the many-body wave function, and so the story widens. Entanglement is not only a bridge between two photons or two qubits, it is the invisible architecture underlying entire phases of matter. The same principle that links distant particles in Bell tests also binds electrons into superconducting pairs and organizes topological states in quantum Hall systems. From the smallest scales to the properties of bulk materials, entanglement remains woven into the fabric of physical reality. Despite the remarkable progress linking entanglement, geometry, and information, a complete theory of quantum gravity remains unfinished. The challenge is clear in outline. Quantum mechanics governs the very small. General relativity governs the very massive and the structure of spacetime itself. Both are experimentally confirmed within their domains. Yet their mathematical frameworks are profoundly different. Quantum mechanics is built on Hilbert spaces, linear operators, and probabilistic amplitudes. General relativity describes a smooth spacetime manifold whose curvature responds to energy and momentum. Reconciling these pictures into a single coherent framework has occupied theoretical physics for decades. One major approach is loop quantum gravity, developed in part by Abhay Ashtekar and collaborators beginning in the 1980s. Loop quantum gravity reformulates general relativity using new variables, known as Ashtekar variables, which recast the gravitational field in terms resembling gauge theory. In this framework, spacetime geometry itself becomes quantized. Instead of a smooth continuum, area and volume operators have discrete spectra. Space is described by spin networks, graphs whose edges and nodes carry quantum numbers. These spin networks represent quantum states of geometry. The fundamental idea is that geometry is not infinitely divisible. At extremely small scales, on the order of the Planck length, roughly 1.6 times 10 to the minus 35 meters, space may consist of discrete quanta. The Planck area and Planck volume emerge as natural scales in this theory. Entanglement plays a role here as well. Spin network states encode relational information between nodes. The connectivity of the graph determines geometric relations. In this picture, geometry arises from combinatorial and algebraic structures, rather than from a smooth background manifold. Loop quantum gravity remains a mathematically consistent and actively researched approach. It has had partial success in deriving black hole entropy, in agreement with the Bekenstein-Hawking area law under certain assumptions. However, it has not yet produced experimentally testable predictions distinguishing it clearly from other approaches. Another proposal is causal set theory, developed by Raphael Sorkin and colleagues. Causal set theory begins from a different starting point. It posits that spacetime is fundamentally discrete, and that its basic structure is a partially ordered set of events connected by causal relations. In this view, spacetime is not a continuous manifold, but a collection of discrete elements ordered by causality. The number of elements corresponds to spacetime volume, and the ordering encodes causal structure. Geometry, including curvature, would emerge statistically from the distribution of these elements. Causal set theory preserves the central role of causality from general relativity, while introducing discreteness at the most fundamental level. It avoids assuming a background geometry, and instead builds space-time from elementary events. Like loop quantum gravity, causal set theory remains under development. It offers conceptual clarity about discreteness and causality, yet connecting it to established low-energy physics and deriving concrete experimental signatures remains challenging. Emergent spacetime hypotheses take a broader perspective. Inspired by holography and entanglement entropy results, some researchers propose that spacetime itself emerges from quantum entanglement, or from more abstract informational structures. In these views, spacetime is not fundamental. It is a large-scale approximation arising from deeper degrees of freedom. Entanglement patterns determine connectivity. Geometry reflects information flow. This idea aligns with earlier discussions of the anti-de Sitter/conformal field theory correspondence and tensor network models. However, extending these insights beyond idealized anti-de Sitter settings to our expanding universe with a small positive cosmological constant remains unresolved. All these approaches face significant experimental limitations. Quantum gravity effects are expected to become significant at the Planck scale. The Planck energy corresponds to approximately 10 to the 19 giga-electron volts. For comparison, the Large Hadron Collider at CERN reaches energies on the order of 10 to the 4 giga-electron volts. The gap spans 15 orders of magnitude. Directly probing Planck-scale physics with particle accelerators is currently beyond technological reach. Some researchers search for indirect signatures. Possible avenues include tiny deviations in the propagation of high-energy cosmic rays modifications of black hole evaporation, or imprints in the cosmic microwave background. So far, no unambiguous experimental evidence for quantum gravity has been confirmed. Conceptual tensions remain as well. One major tension concerns the problem of time. In canonical approaches to quantum gravity, such as loop quantum gravity, the Wheeler-DeWitt equation describing the quantum state of the universe lacks an explicit time parameter. This leads to deep questions about how temporal evolution emerges from a fundamentally timeless formalism. Another tension involves the black hole information paradox. If black holes evaporate completely through Hawking radiation, what happens to the information about the matter that formed them? Unitarity in quantum mechanics demands information conservation. Early semi-classical calculations suggested information loss. More recent developments, including holographic insights and calculations of so-called page curves, indicate that information may be preserved in subtle correlations within Hawking radiation. Yet a complete consensus remains elusive. There is also the challenge of background independence. General relativity treats spacetime geometry as dynamical. Many quantum field theories, by contrast, are formulated on fixed backgrounds. A fully satisfactory quantum gravity theory should ideally avoid presupposing a fixed spacetime stage. Each proposed framework addresses some aspects of these tensions while leaving others open. The landscape is therefore one of active exploration rather than settled doctrine. Loop quantum gravity quantizes geometry directly. Causal set theory discretizes spacetime events. Holographic approaches suggest spacetime emerges from entanglement. String theory, though not detailed here, introduces additional dimensions and extended objects. No approach has yet achieved comprehensive experimental confirmation. This uncertainty is not a failure. It reflects the extraordinary difficulty of unifying two of the most successful theories in physics. Both quantum mechanics and general relativity have been tested with extraordinary precision in their respective domains. Bridging them requires navigating scales and regimes far removed from everyday experience. Entanglement remains central in many of these efforts. Whether through holographic dualities, spin networks, or entanglement entropy calculations, quantum correlations appear deeply intertwined with geometry. The unresolved conceptual tensions serve as reminders that the story is not complete. The connections between information, space-time, and gravity are compelling but not yet fully understood. What is clear is that entanglement is not an isolated phenomenon confined to laboratory experiments. It reaches into the structure of matter, the emergence of classical reality, and the fabric of space-time itself. The final answers about quantum gravity remain beyond our current experimental horizon, yet the questions themselves continue to refine our understanding of how distant things might stay connected at the deepest levels of physical law. How can distant things stay connected? After all the equations, experiments, interpretations, and speculative bridges between space-time regions, the question returns in its simplest form. Two systems move apart. Kilometers may separate them. Light may take measurable time to travel between them. Yet when measurements are performed, correlations appear that no classical local model can reproduce. The answer is not that a hidden signal flashes across space at superluminal speed. The no-signaling theorem ensures that no controllable information travels faster than light. Special relativity, established in 1905 and tested repeatedly through particle physics and satellite navigation, remains intact. The answer is more structural. Entangled systems share a single quantum state. That state is described mathematically in a Hilbert space formed by the tensor product of the subsystems. If the state cannot be factorized into independent parts, then the systems are not independent in the classical sense, even if they are spatially separated. The connection lies in the joint structure. When a pair of particles is prepared in a singlet spin state, for example, the total spin is defined even though the individual spins are not. The state encodes relational information. Measuring one particle reveals something about the other because both are described by a single, inseparable quantum state. Nothing is transmitted at the moment of measurement. Instead, the correlation was encoded at preparation. John Bell's theorem in 1964 demonstrated that no theory based on local hidden variables can reproduce the correlations predicted by quantum mechanics. The Clauser-Horn-Schimmony-Holt inequality quantified that limit. Experiments by Alain Aspect in the early 1980s, followed by increasingly refined tests by Anton Zeilinger, Ronald Hansen, and teams at the National Institute of Standards and Technology, consistently observed violations of the classical bound. The measured values approach the quantum limit of approximately 2.828, Zerelson's bound. They do not exceed it. The data align with quantum predictions and reject local realism in the EPR sense. This empirical confirmation has accumulated over decades, across laboratories, across continents, and even through satellite-based experiments led by Jean-Wei Pan. The conclusion is steady and robust. Entanglement is real. The structural perspective clarifies why this does not contradict relativity. The reduced density matrix describing one subsystem remains unchanged by measurement choices performed on the other. Local statistics are unaffected. Correlations appear only when results are compared through ordinary communication. Thus, entanglement reflects shared structure, not exchange signals. The informational perspective adds another layer. Entanglement distributes information across subsystems. The von Neumann entropy of a subsystem increases when it becomes entangled with its partner. Information about the whole is not stored locally, it resides in correlations. In quantum information theory, entanglement becomes a resource. It enables quantum key distribution, teleportation, and computational speedup. It can be quantified through measures such as concurrence. It can be distilled and manipulated under the constraints of local operations and classical communication. From this viewpoint, distant systems remain connected because they participate in a single, informational structure. The classical idea that each subsystem carries its own complete set of properties is replaced by a relational description. The geometric perspective extends the idea further. In quantum field theory, even the vacuum is entangled across space-like regions. The Ray-Schlieder theorem reveals that local operations can approximate global states because the vacuum itself is highly correlated. In holographic dualities, entanglement entropy in a boundary theory corresponds to geometric surfaces in a higher dimensional spacetime. The Ryutaka-Yanagi formula ties entropy to area. The ER equals EPR conjecture suggests that entanglement may correspond to geometric connectivity, such as Einstein-Rosen bridges. These developments do not imply that laboratory particles are joined by traversable tunnels. They suggest that connectivity in quantum states may have geometric interpretation at deeper levels of description. Across structural, informational, and geometric viewpoints, a common theme emerges. Classical separability is not fundamental. In classical mechanics, the state of a composite system is simply the collection of the states of its parts. In quantum mechanics, the state of the whole may contain correlations that are irreducible to individual descriptions. Independence becomes approximate. Decoherence explains why classical independence appears in everyday life. Entanglement with the environment suppresses interference between macroscopically distinct states. Pointer states become stable. Redundant encoding of information through quantum Darwinism produces objective classical outcomes. At large scales, objects behave as if they possess independent properties. That behavior is real and reliable. It is simply emergent rather than fundamental. The tension that troubled Einstein was not about faster-than-light signaling alone. It was about the idea that distant systems should have independent real states. Quantum mechanics revises that assumption. It does so without abandoning empirical discipline. The predictions are precise, the correlations are measured, the limits are defined, the mathematics is coherent. How can distant things stay connected? Because at the quantum level, distance does not guarantee independence. Systems that have interacted may share a joint state that persists even when they move apart. The connection is encoded in that state. The world is not composed of isolated fragments stitched together only by local forces. It is structured by patterns of correlation that sometimes extend beyond classical boundaries. This does not dissolve causality. It does not permit arbitrary influence across space. It reframes the notion of what it means to be separate. The classical picture of distinct objects with intrinsic properties remains extraordinarily useful at everyday scales. It emerges from decoherence and environmental entanglement. But beneath that layer lies a deeper description in which relations precede isolated attributes. Entanglement is not an anomaly. It is a window into that deeper structure. Distant things remain connected because in certain states they were never fully separate to begin with. And that conclusion, supported by decades of experiment and guided by consistent mathematics, invites a quieter shift in perspective. Perhaps connection is not something that travels across space. Perhaps it is something that space itself reflects. Quantum entanglement expresses something precise and radical about physical law. It tells us that the state of a composite system is not always reducible to the states of its parts. Non-separability is not a philosophical add-on. It is written directly into the mathematical structure of quantum theory through the tensor product of Hilbert spaces and the existence of non-factorizable states. This feature has been tested repeatedly. From John Bell's theorem in 1964 to the experiments of Alain Aspect in the early 1980s, and through increasingly refined tests by Anton Zeilinger, Ronald Hansen, and research groups at the National Institute of Standards and Technology, the empirical verdict has been consistent. Nature violates classical inequalities. Quantum predictions are confirmed within experimental precision. No faster-than-light signaling is observed. Relativistic causality remains intact. Theory, experiment, and information structure align. The formalism of quantum mechanics predicts entanglement. Laboratory measurements verify it. Quantum information theory quantifies and exploits it. Quantum field theory embeds it into the vacuum itself. Holographic dualities suggest it may even underpin aspects of geometry. Across these domains, the same principle appears. The whole can possess structure that no list of independent parts can fully capture. At the same time, caution is essential. Not every speculative extension has been confirmed. Proposals in quantum gravity, including holographic conjectures and emergent spacetime hypotheses, remain areas of active research. They are mathematically motivated and internally consistent in specific models, but direct experimental evidence at Planck scale energies is beyond current technological reach. The frontier is real, and so are its limits. What is not uncertain is the core phenomenon. Entanglement is measured, engineered, and harnessed. It secures communication. It shapes materials. It defines correlations that classical theories cannot reproduce. Classical separability, so intuitive and reliable in daily life, emerges from decoherence and environmental interactions. It is an effective description, not the deepest layer. Beneath it lies a relational structure in which systems can share a joint state across space without exchanging signals at the moment of measurement. Distance remains meaningful. Causality remains ordered. Yet independence is conditional. Quantum entanglement does not dissolve the world into mystery. It refines the picture. It shows that connection can be structural rather than dynamic, encoded in the state rather than carried by a message. In that sense, distant things stay connected because physical reality permits states that transcend classical partitions. The universe allows correlations that respect relativity while defying classical separability. The result is not paradox, but coherence at a deeper level. Connection and distance coexist within a single, consistent framework, and that framework, built from experiment and mathematics, continues to guide the search for an even more unified understanding of physical reality.